Look up on a moonless autumn night, away from the city lights, away from the glow of civilization. Your eyes will adjust to the darkness. And there, in the constellation Cassiopeia, you'll see it. A faint, fuzzy smudge. Nothing dramatic, nothing that screams for your attention. Just a subtle patch of light that looks like a cosmic thumbprint on the velvet blackness of space. This is what our ancestors saw. Thousands of years ago, ancient Persian astronomers noticed this peculiar blur and called it the Little Cloud. They had no idea what they were looking at, no concept of its true nature. To them, it was just another mystery in a sky full of mysteries. Here's what's remarkable. If you could see Andromeda's full extent, if your eyes could detect all the light it's sending our way, it would span an area roughly 6 times the width of the full moon. 6 times. That's enormous. The galaxy is actually covering a significant portion of our night sky right now, at this very moment. But we can't see it. Most of it is simply too dim for our eyes to register. What we perceive is only the brightest central core, a tiny fraction of the whole structure. It's like looking at an iceberg and seeing only the tip while the massive bulk remains hidden beneath the surface. Except in this case, the invisible portions aren't underwater. They're just too faint to trigger our retinas. And here's the tragedy of our modern world. Most people on Earth have never seen Andromeda. Not because it's not there, not because it's hiding, but because we've drowned it out. Light pollution from our cities, our streets, our homes creates a perpetual artificial twilight that washes out everything subtle in the night sky. We've traded the cosmos for convenience, and in doing so, we've lost touch with something our ancestors took for granted. In a truly dark location, far from any human settlement, Andromeda is visible to the naked eye as magnitude 3.4 object. That might not sound impressive, but it means that under pristine conditions, it's actually quite noticeable once you know where to look. It's right there, in the northern sky, waiting. 2.5 million light-years away, yet visible without any equipment whatsoever. Think about that for a moment. The most distant object you can see with your naked eye. No telescope, no binoculars, just your eyes and the darkness. That faint smudge represents the edge of what's accessible to human vision across the cosmic void. Everything beyond it requires technology to perceive. Our ancestors saw this light and wondered. They couldn't have known they were looking at another galaxy. They couldn't have conceived of the distances involved, the scale, the sheer number of stars generating that soft glow. But they noticed it. They recorded it. They passed down knowledge of its existence through generations. And now, most of us live under skies so bright that we've become blind to it. 2.537 million light-years. That's the distance to Andromeda. But what does that number actually mean? Let's break it down, because the human brain isn't equipped to grasp this kind of scale intuitively. Light travels at 299,792 kilometers per second. That's fast enough to circle the Earth 7.5 times in 1 second. Fast enough to reach the Moon in about 1.25 seconds. Fast enough to cross our entire solar system, from the Sun to Pluto, in about 5.5 hours. Light is the ultimate speed demon of the universe. Nothing moves faster. Nothing can move faster. And yet, it takes light 2.5 million years to reach us from Andromeda. Let that sink in. The light entering your eyes when you look at Andromeda tonight began its journey 2.537 million years ago. Not 2.537 years. Not 2.537 thousand years. 2.5 million years. The photons striking your retina are older than our species, older than our genus. They're ancient beyond human comprehension. When that light left Andromeda, humans didn't exist, not even close. Our ancestors at that time were Homo habilis, early members of our genus, yes, but barely recognizable as related to us. They stood about 4 feet tall. Their brains were roughly half the size of ours, They were just beginning to figure out how to chip rocks into crude tools. There was no language as we understand it, no art, no culture, no cities, no agriculture, no writing, no civilization. These were creatures who lived in small groups, scavenging and hunting, struggling to survive in an African landscape dominated by predators far more formidable than themselves. That's what Earth was like when the light you're seeing tonight began its journey. And for the entire span of that journey, traveling at the maximum possible speed through the vacuum of space, that light has been racing toward us. Through the void, through the emptiness, covering 6 trillion miles every single year, year after year, for 2.537 million years. Let's put it another way. If you could somehow travel at the speed of light, which is impossible, but bear with me, and you started your journey from Earth right now, you wouldn't arrive at Andromeda until the year 2,539,526 AD. And during that entire journey, traveling faster than anything can possibly travel, you'd be crossing empty space, just darkness and distance. The space between us and Andromeda isn't filled with anything. It's not like crossing an ocean where you encounter water the whole way. It's void, true emptiness, just the occasional atom of hydrogen drifting through the intergalactic medium. You could fit millions of solar systems in the gap between our galaxy and Andromeda, and there'd still be room left over. Now here's where it gets even more mind-bending. Because Andromeda is moving toward us, the light we're seeing doesn't represent where Andromeda is now. It represents where Andromeda was 2.537 million years ago. The galaxy has moved since then. It's currently about 140,000 light-years closer to us than it appears to be. We're not seeing the present version of Andromeda. We're seeing a ghost, an echo from the deep past. When we look at Andromeda, we're literally looking backward in time. We're seeing ancient history playing out in real time, except the now we're observing happened when our ancestors were barely human. And here's the kicker. If there's an alien astronomer on a planet in Andromeda looking at the Milky Way right now, they're not seeing us. They can't be. The light from our current era hasn't reached them yet. They're seeing Earth as it was 2.537 million years ago. They're seeing a planet with no humans, no cities, no technology, just wilderness and wildlife. We are separated not just by distance, but by time itself. The cosmic speed limit ensures that we can never see each other as we truly are in the present moment. We're looking at each other's past, and we always will be. This is the first lesson in understanding Andromeda's true scale. The distance alone is enough to break your brain, and we're just getting started. For thousands of years, humanity looked at Andromeda and had no idea what it was. A cloud, a nebula, something in the sky. The details didn't matter because we lacked the tools to investigate further. But by the early 20th century, that was changing. Telescopes were getting bigger. Photography was allowing astronomers to capture details invisible to the eye. And a question emerged that would fundamentally reshape our understanding of the universe. Was Andromeda part of our galaxy, or was it something else entirely? This might seem like an academic question, the kind of thing only astronomers would care about. But the answer would determine whether we lived in a universe that was essentially just one galaxy, with everything we could see belonging to the Milky Way, or whether we lived in a universe filled with countless separate galaxies, each one a massive island of stars floating in an incomprehensibly larger cosmos. The stakes couldn't have been higher. This was about the fundamental nature of reality. By 1920, the astronomical community was split into two camps. On one side were those who believed the universe was essentially synonymous with the Milky Way. They looked at fuzzy patches like Andromeda, which they called spiral nebula, and assumed they were clouds of gas within our own galaxy, maybe places where stars were forming, maybe planetary systems in development, but definitely part of our cosmic neighborhood. On the other side were those who proposed something far more radical. They suggested that these spiral nebulae were actually separate galaxies, so distant that individual stars blurred together into a soft glow. They called them island universes, each one potentially as large as the Milky Way itself, containing billions of stars floating in the void of intergalactic space. The debate came to a head on April 26, 1920, at the Smithsonian Museum of Natural History in Washington, D.C. Two astronomers, Harlow Shapley and Heber Curtis, presented opposing views in what would later be called the Great Debate. Shapley argued that spiral nebulae were part of our galaxy. He presented evidence that seemed to support this view, including measurements that suggested these objects were relatively small and relatively close. He painted a picture of a universe contained within one enormous galaxy, with the Milky Way representing essentially everything that existed. Curtis argued the opposite. He presented evidence that spiral nebulae showed properties consistent with being separate galaxies. They rotated like galaxies should rotate. They had similar structures to what we could deduce about our own galaxy. And most importantly, they seemed to be incredibly distant based on their apparent brightness and size. The debate ended without a clear winner. Both sides had compelling arguments. Both sides had evidence. The astronomical community remained divided. But then, just a few years later, the answer came. And it came from an astronomer named Edwin Hubble, working with the most powerful telescope in the world at the time, the 100-inch Hooker telescope at Mount Wilson Observatory in California. Hubble was studying Andromeda, photographing it night after night, looking for details that might settle the question once and for all. And in 1923, he found something extraordinary. He identified individual stars within Andromeda, not just any stars, but a specific type called Cepheid variables. Cepheid variables are stars that pulse with a regular rhythm, getting brighter and dimmer in a predictable pattern. And here's what makes them invaluable. There's a direct relationship between how fast they pulse and how bright they actually are. By measuring the pulse rate, you can calculate the star's true luminosity. And once you know how bright it actually is, versus how bright it appears from Earth, you can calculate exactly how far away it is. Hubble measured the Cepheids in Andromeda. He did the math. And the answer was staggering. Andromeda wasn't just outside our galaxy. It was nearly 1 million light-years away, far, far beyond the boundaries of the Milky Way. The island universe theory was correct. Andromeda was a separate galaxy. And if Andromeda was a separate galaxy, then all those other spiral nebulae scattered across the sky were probably separate galaxies too. The universe wasn't one galaxy. It was countless galaxies. The Milky Way was just one among multitudes, perhaps billions. Each one an enormous collection of stars separated from its neighbors by vast gulfs of empty space. This discovery ranks among the most important in human history. In one observation, Hubble expanded the known universe by orders of magnitude. We went from living in a galaxy to living in a universe of galaxies. Our cosmic address got a lot more complex. Before 1923, Earth, Solar System, Milky Way, Universe. After 1923, Earth, Solar System, Milky Way, Local Group, Universe. And we'd soon discover that the structure went even deeper than that, with galaxy clusters, superclusters, and cosmic web filaments stretching across billions of light-years. The Great Debate was settled. The universe was unimaginably larger than we'd thought. And Andromeda, that faint smudge visible to the naked eye, was the key that unlocked this new understanding. It was our first glimpse beyond our cosmic home, our first confirmation that we were not alone in the universe, at least in terms of galaxies. Everything changed in 1923. And it all started with measuring the distance to Andromeda. So we've established that Andromeda is 2.537 million light-years away. That's the distance. But now let's talk about size, because distance is one thing, scale is another. And when it comes to Andromeda's actual dimensions, the numbers become almost absurd. Andromeda stretches 220,000 light-years from edge to edge, 220,000 light-years. That's the diameter of the visible disk, the main structure of the galaxy where most of the stars reside. To put that in perspective, the Milky Way is approximately 100,000 light-years across, maybe 105,000 depending on where you draw the boundaries. Andromeda is more than twice as wide. It's the largest sibling in our cosmic family, the dominant galaxy in our local group. But let's break down what 220,000 light-years actually means, because just saying the number doesn't convey the scale. Remember, 1 light-year is about 6 trillion miles. It's the distance light travels in a full year at 186,000 miles per second. So 220,000 light-years is roughly 1.3 quintillion miles. That's 1 quintillion 300 and quadrillion miles. A 1 followed by 18 zeros. If you tried to count to 220,000, saying one number per second, it would take you about 2.5 days. Now imagine each one of those numbers represents a light year, represents 6 trillion miles. The scale becomes incomprehensible very quickly. Let's try another comparison. Our entire solar system, from the Sun to the outer reaches of the Oort cloud, is roughly 1 light-year across, maybe a bit more. So you could fit 220,000 solar systems lined up edge to edge across the diameter of Andromeda. And remember, each solar system in that line would include all the space out to the comet cloud, the entire gravitational domain of the star. Here's another way to think about it. If you were somehow traveling at 1 million miles per hour, which is spectacularly fast by any human standard, it would take you 148 years just to cross 1 light-year. To cross Andromeda's full diameter at that speed would take 32.5 million years, 32.5 million years of continuous travel at 1 million miles per hour. The fastest spacecraft humanity has ever built is the Parker Solar Probe, which reaches speeds of about 430,000 miles per hour at its closest approach to the Sun. At that speed, crossing Andromeda would take roughly 344 million years. That's longer than the entire time dinosaurs existed on Earth. Now let's compare Andromeda to some other cosmic structures to give you a sense of where it fits in the hierarchy of scale. The distance from Earth to the Sun is about 93 million miles. We call this an astronomical unit, or AU. It's a useful measuring stick within our solar system. Andromeda's diameter is roughly 23 billion AU. That's billion with a B. The nearest star to our Sun, Proxima Centauri, is 4.24 light-years away. You could fit about 52,000 of those distances across Andromeda's width. The distance from one side of the Milky Way to the other is about 100,000 light-years. Andromeda is 2.2 times wider. If the Milky Way were the size of the United States, Andromeda would stretch from Alaska to Brazil. The total volume is even more staggering. Volume increases with the cube of the diameter, so even though Andromeda is only 2.2 times wider than the Milky Way, its volume is more than 10 times greater. If both galaxies were spheres, which they're not, but bear with me, Andromeda would have about 10.6 times more space inside it than the Milky Way. And here's something that really puts it in perspective. Even though Andromeda is 220,000 light-years across, and even though it's the largest galaxy in our local group, it's actually not that big compared to some of the monster galaxies out there in the wider universe. There are elliptical galaxies in distant galaxy clusters that span over 1 million light-years. IC 1101, one of the largest known galaxies, has a diameter of approximately 6 million light-years. That's more than 27 times wider than Andromeda. The universe has structures that make even Andromeda look small. But in our cosmic neighborhood, in the local group of galaxies that includes the Milky Way, Andromeda is the giant. It's the dominant gravitational force. It's the biggest structure around. And when you consider that this enormous disk of stars, gas, and dust is all held together by gravity, all rotating around a common center, all functioning as a single coherent structure, the engineering of it becomes mind-boggling. Gravity has to reach across 220,000 light-years to hold this thing together. Stars on opposite sides of the galaxy are so far apart that light from one side takes 220,000 years to reach the other. And yet they're all bound to the same structure, all orbiting the same center, all part of the same galactic dance. The scale of Andromeda isn't just big. It's a monument to what gravity can accomplish given enough matter and enough time. It's a structure so large that human minds can barely wrap around it, and yet it's all right there, visible in our night sky, waiting for anyone with clear skies and dark enough conditions to look up and see it. Andromeda contains approximately 1 trillion stars. That's 1 trillion individual suns. Let's make that number mean something, because just saying a trillion doesn't convey the absurdity of what we're talking about. First, compare that to the Milky Way. Our galaxy contains somewhere between 200 and 400 billion stars, with most estimates settling around 250 to 300 billion. Andromeda has roughly 3 to 4 times as many. It's not just bigger in diameter, it's more densely populated with stars. Now, a trillion is a number we throw around these days, especially when talking about government budgets or global economics. But when applied to physical objects, to individual stars each representing an entire solar system, the number becomes surreal. If you started counting right now, one number per second, without stopping to sleep or eat or do anything else, it would take you 31,688 years to count to 1 trillion. That's longer than all of recorded human history. The pyramids were built only about 4,500 years ago. Writing was invented maybe 5,000 years ago. You'd have to count through the entire span of human civilization 6 times over just to reach a trillion. Here's another way to grasp it. If every star in Andromeda were a grain of sand, you'd have enough sand to cover the entire surface area of a football field to a depth of about 100 feet. Picture that. A football field with sand piled as high as a 10-story building. That's how many stars we're talking about. If you wanted to visit every star in Andromeda, spending just 1 second at each star before moving to the next, it would take 31,688 years, 1 second per star. Not enough time to even get a good look at any of them. Just a brief moment, then on to the next. And it would still take longer than the entire history of human civilization. Let's think about this in terms of the night sky. On a perfectly clear, dark night, far from any light pollution, the human eye can see approximately 4,500 stars. That's the total number visible to the naked eye across the entire celestial sphere. Andromeda contains about 222 million times more stars than you can see with your eyes from Earth. If every star in Andromeda were visible in our night sky, and they were all spread out evenly, you'd see about 13 million stars in every square degree of sky. The entire sky would be nothing but a solid sheet of light. Now let's talk about what kinds of stars make up this trillion. Because they're not all the same. Stars come in different sizes, different colors, different temperatures, different lifespans. Andromeda has the full spectrum. There are red dwarfs, the smallest and most common type of star. These are tiny, dim things that burn their fuel so slowly they can last for trillions of years. They make up probably 7080% of Andromeda's stellar population, which means there are somewhere around 700 to 800 billion red dwarfs in Andromeda alone. There are stars like our Sun, yellow main sequence stars in the middle of their lives, quietly fusing hydrogen into helium. Andromeda probably has tens of billions of these. There are red giants, stars that have exhausted their core hydrogen and swelled up to enormous sizes. Some of these are so large that if you placed them where our Sun is, they'd extend past Earth's orbit. Andromeda has millions, maybe billions of these. There are blue supergiants, monsters dozens of times more massive than the Sun, burning through their fuel at such an incredible rate that they'll only live a few million years before exploding as supernovae. These are rare, but in a galaxy of 1 trillion stars, rare still means millions of them exist. There are white dwarfs, the collapsed cores of dead stars, each one about the size of Earth but with roughly the mass of the Sun, packed so densely that a teaspoon of white dwarf material would weigh several tons. Andromeda likely has hundreds of billions of these, the remnants of stars that died billions of years ago. There are neutron stars, even denser than white dwarfs, the crushed remnants of stars that exploded as supernovae. Some of these spin at hundreds of rotations per second, beaming out radiation like cosmic lighthouses. Andromeda probably has tens of millions of these scattered throughout its structure. And there are black holes. Stellar mass black holes, formed from the most massive stars, each one representing a point where a star's core collapsed so completely that it punched a hole in space-time itself. Current estimates suggest Andromeda might contain 100 million stellar mass black holes, each one between 3 and 100 times the mass of the Sun. Every single one of these stars is a complete, individual object. Every one is undergoing nuclear fusion, or has undergone it in the past. Every one has its own properties, its own history, its own eventual fate. Many of them likely have planets. Some of those planets might harbor life. If even 10% of the stars in Andromeda have planets, that's 100 billion planetary systems. If even 1% of those have conditions potentially suitable for life, that's 1 billion potentially habitable worlds. The numbers become staggering very quickly. And here's what really breaks your brain. Every single star in Andromeda is moving. They're not fixed in place. They're all in orbit around the galactic center, completing one full rotation every 200 to 250 million years or so. That means the entire structure is dynamic, constantly shifting, 1 trillion objects all moving in their own orbits, while remaining gravitationally bound to the whole. It's a dance on an incomprehensible scale, a choreography involving 1 trillion participants, all moving through space in response to the combined gravitational pull of every other object in the galaxy, along with the dark matter we'll talk about later. 1 trillion stars. It's not just a number. It's 1 trillion individual futures, 1 trillion different evolutionary paths, 1 trillion points of light that have been shining for billions of years and will continue to shine for billions more. And all of it, every single star, is visible to us as a faint smudge in the night sky. Here's where things get weird. Andromeda has roughly 3 to 4 times as many stars as the Milky Way. It's twice as wide. It has more volume. By every visible metric, it's the bigger galaxy. And yet, when you actually measure the total mass of both galaxies, they're approximately the same. Both the Milky Way and Andromeda weigh in at around 1.5 trillion solar masses. That's the combined mass of everything in each galaxy. All the stars, all the gas, all the dust, all the black holes, everything. And the numbers are nearly identical despite the dramatic difference in star count. How is that possible? The answer is dark matter, and it's one of the deepest mysteries in modern astrophysics. Let's start with what we can see. Andromeda's trillion stars contribute a certain amount of mass. All that gas and dust between the stars adds more. The supermassive black hole at the center adds its contribution. When you add all the visible matter together, you get somewhere around 200,300 billion solar masses. That's a lot of mass, but it's not 1.5 trillion. The Milky Way's visible matter totals roughly the same, maybe a bit less given that we have fewer stars. Again, 200,300 billion solar masses of stuff we can actually detect and measure. So where's the rest of the mass? Where's the other 1.2 trillion solar masses in each galaxy that we can't see? It's dark matter. Material that doesn't emit light, doesn't absorb light, doesn't interact with electromagnetic radiation in any way we can detect. It's invisible. The only way we know it's there is through its gravitational effects, and those effects are undeniable. When astronomers measure how fast stars are orbiting in Andromeda and the Milky Way, the speeds don't match what they should be based on the visible matter alone. Stars on the outer edges of galaxies are moving way too fast. According to the laws of gravity and the amount of matter we can see, those stars should be flying off into intergalactic space. The visible matter doesn't generate enough gravity to hold them in orbit, but they're not flying away. They're staying in orbit, which means there must be additional mass, additional gravity holding them in place. Mass we can't see. This is the dark matter halo. Every galaxy is surrounded by an enormous sphere of invisible material that extends far beyond the visible disk. In Andromeda's case, this halo probably extends out to 500,000 light-years or more from the galactic center, more than twice the diameter of the visible galaxy. And it's not just a little bit of dark matter, it's the dominant component of the galaxy's mass. Roughly 5% of each galaxy's total mass is dark matter. The stars, the gas, the dust, all the stuff we can see and measure, that's only 1520% of what's actually there. Think about that. When you look at Andromeda, you're seeing less than 1/5 of what's actually present. The majority of the galaxy is completely invisible, detectable only through its gravitational influence on the matter we can see. Now, what is dark matter? Honestly, we don't know. It's one of the biggest unsolved problems in physics. We know it's there. We can measure its effects. We can map its distribution. But we have no idea what it's actually made of. It's not regular matter, just dark. It's not clouds of gas too cold to glow. It's not black holes or planets or failed stars. We've ruled all those out. It's something else, something exotic, particles that don't interact with light at all, passing through regular matter as if it weren't there, influencing the universe only through gravity. Current theories suggest it might be WIMPs, weakly interacting massive particles, or maybe axions, or maybe some form of matter we haven't even theorized yet. Experiments around the world are trying to detect dark matter directly, trying to catch one of these particles as it passes through their detectors. So far, no confirmed detections. But here's what we know about dark matter in Andromeda specifically. The halo isn't uniform. It's denser near the center and less dense toward the edges. It forms a roughly spherical distribution, unlike the flat disk of stars and gas. And it's absolutely essential to Andromeda's structure. Without dark matter, Andromeda wouldn't exist as we see it. The galaxy would have torn itself apart billions of years ago, its stars flying off into space because there wasn't enough gravity to hold them together. The fact that Andromeda is a stable rotating disk is proof that dark matter is real and present in enormous quantities. The same is true for the Milky Way. Our galaxy is also embedded in a massive dark matter halo. We're swimming through dark matter right now. Billions of dark matter particles are passing through your body every second. You don't feel them because they barely interact with regular matter at all. But they're there, and their collective gravity is what keeps our galaxy and every other galaxy intact. So when we say Andromeda and the Milky Way have similar masses, we're talking about the total mass, including this invisible component. And the fact that both galaxies have roughly the same total mass, despite Andromeda having more visible matter, is actually really interesting. It suggests that the ratio of dark matter to regular matter might not be the same in both galaxies. Andromeda might have a slightly less massive dark matter halo relative to its visible matter. Or the Milky Way might have more dark matter than we thought. Or our measurements might be slightly off. This is cutting-edge research. Astronomers are still refining their measurements, still trying to map out exactly how dark matter is distributed in both galaxies. But what's clear is that when we talk about the mass of a galaxy, we're talking about something that's mostly invisible, mostly unknown, and absolutely fundamental to how galaxies form and evolve. Andromeda and the Milky Way, despite their differences in size and star count, are remarkably similar when you account for everything that's there, both seen and unseen. They're twin giants, each dominated by a mysterious substance we can't directly detect, held together by gravity, floating through space on a collision course that will unite them billions of years from now. Andromeda is a spiral galaxy. When you see pictures of it, you can make out the graceful arms curving out from the central bulge, sweeping through space in elegant arcs. But what exactly are these spiral arms, and what's happening inside them? First, let's be clear about what spiral arms are not. They're not solid structures. They're not like the arms of a starfish, physically attached to a central body. The stars in Andromeda aren't locked into the spiral pattern. If you could mark individual stars and watch them orbit over millions of years, you'd see them drift in and out of the spiral arms, moving through them like cars moving through a traffic jam. Because that's essentially what spiral arms are. They're density waves, regions where stars, gas, and dust bunch up temporarily due to gravitational interactions. Think of them as traffic jams on a cosmic highway. The cars, stars, move through the jam, slow down while they're in it, then speed up and move out the other side. But the jam itself, the compressed region, remains roughly in the same place. Andromeda has at least two major spiral arms, though the exact structure is still being mapped and debated. Some observations suggest there might be additional, fainter arms or arm fragments. The spiral pattern wraps around the galaxy, creating that distinctive pinwheel shape we associate with spiral galaxies. The arms are rich in gas and dust. This is crucial because gas and dust are the raw materials for star formation. When the density wave passes through a region of the galaxy, it compresses the gas clouds there. That compression can trigger collapse, causing the gas to condense and form new stars. This is why spiral arms glow so brightly in photographs. They're full of young, hot, massive stars that formed recently from the compressed gas. These stars are blue and incredibly luminous, pumping out enormous amounts of light and ultraviolet radiation. They only live a few million years before exploding as supernovae, but while they're alive, they're beacons marking the locations of active star formation. The spiral arms also contain vast clouds of hydrogen gas that glow red in many images. This is emission from hydrogen atoms being excited by the ultraviolet radiation from all those young stars. The hydrogen absorbs the UV light, then re-emits it at specific wavelengths, creating the reddish glow you see in detailed photographs of Andromeda. Between the spiral arms, the galaxy is darker but not empty. This is where most of the stars actually are. Older stars, yellow and red stars like our Sun, or smaller, stars that formed billions of years ago and have settled into long, stable lifespans. They don't glow as brightly as the young blue stars in the arms, so they're less visible in photographs, but they represent the bulk of the stellar population. Dust lanes trace the inner edges of the spiral arms. These are thick bands of cosmic dust, tiny particles of carbon, silicon, and other elements that block visible light. Where you see dark regions in images of Andromeda, that's usually dust. It's not that there's nothing there, it's that the dust is blocking the light from stars behind it. But look at Andromeda in infrared, and those dust lanes light up. Dust absorbs visible and ultraviolet light and re-emits it as infrared radiation. So in infrared images, the dustiest parts of the spiral arms glow brightly, revealing details invisible in regular photographs. The spiral structure isn't static, it's rotating, but not like a solid object. Different parts of the galaxy rotate at different speeds. The inner regions complete their orbits faster than the outer regions. This differential rotation is part of what maintains the spiral pattern. If the galaxy rotated like a solid disk, the spiral arms would wind up tighter and tighter over time, eventually wrapping into a tight spiral. But because different parts rotate at different speeds, and because the density waves propagate through the disk, the spiral pattern can persist for billions of years. Comparing Andromeda's spiral structure to the Milky Way's is tricky, because we're inside the Milky Way and can't get a clear outside view of our own galaxy's structure. But from what we can tell, the Milky Way has a similar spiral pattern, probably 4 major arms plus some smaller arm fragments. We're located between 2 arms in a small spur called the Orion Arm, or local spur. Andromeda's spiral structure is more tightly wound than some spiral galaxies and less tightly wound than others. Astronomers classify spiral galaxies by how tight their arms are, among other features. Andromeda is classified as SASB, or sometimes SB, which indicates it has a moderately tight spiral structure without a prominent bar running through the center. Actually, that's worth explaining. Some spiral galaxies have a bar, an elongated structure of stars running through the central bulge. Our Milky Way has a bar. Andromeda does not, or at least not an obvious one. This affects how gas flows in the galaxy and influences the spiral structure. There's also evidence that Andromeda's spiral structure might be partially triggered by gravitational interactions with its satellite galaxies. When a smaller galaxy passes close to a larger one, the gravitational perturbation can enhance or modify the spiral pattern. Andromeda has experienced several such interactions over its history, and they might have left their mark on the current spiral structure. Supernovae in the spiral arms create expanding shells of hot gas that can trigger additional star formation in the surrounding clouds. So the spiral arms aren't just passive regions of compression, they're active, dynamic environments where star formation begets more star formation, where the life cycles of stars influence each other, where the interstellar medium is constantly being enriched with new elements forged in stellar cores. Every element heavier than hydrogen and helium was created in a star. The oxygen you breathe, the carbon in your body, the iron in your blood, all of it was forged in stellar furnaces and then scattered into space when those stars died. In Andromeda's spiral arms, this process is happening right now. Stars are dying, enriching the gas clouds with heavy elements, and new stars are forming from that enriched material, creating a slow but steady increase in the metallicity of the galaxy over cosmic time. The spiral arms of Andromeda are where the galaxy is most alive, most active, most dynamic. They're the regions where the galaxy's future is being written, where new stars and new planetary systems are coming into existence, where the raw materials of the universe are being cycled through generations of stellar creation and destruction. At the heart of Andromeda lies the central bulge, a densely packed sphere of stars that dominates the inner region of the galaxy. This isn't like the spiral arms we just discussed. This is something fundamentally different in character and composition. The bulge spans roughly 12,000 light-years in diameter. That might sound modest compared to the galaxy's overall size, but don't let the number fool you. This region contains a significant fraction of Andromeda's total stellar mass, packed into a relatively compact volume. The density of stars in the bulge is thousands of times higher than in the spiral disk. If you were standing on a planet in the bulge region, the night sky would be spectacular beyond imagination. Stars would be separated by light weeks instead of light years. The nearest stars would be close enough that they'd appear as actual disks to the naked eye, not just points of light. The sky would be crowded with bright stars in every direction, creating a perpetual twilight even in the depths of night. But you probably wouldn't want to live there. The radiation environment would be harsh. Stellar encounters would be more frequent, occasionally disrupting planetary orbits. And the supermassive black hole at the very center would be an ever-present gravitational monster influencing the motion of everything in the region. The stars in the bulge are old. These aren't the young hot blue stars you find in the spiral arms. These are ancient red and yellow stars, population 2 stars that formed early in the galaxy's history, more than 10 billion years ago. Many of them are older than the Sun. You can tell by their color. Red and yellow stars are cooler than blue stars. They're also older, generally speaking. The massive blue stars that once existed in the bulge have long since exhausted their fuel and died. What remains are the smaller, longer-lived stars that have been quietly fusing hydrogen for billions of years. The metallicity of bulge stars is different from disk stars too. Metallicity, in astronomy, refers to the abundance of elements heavier than hydrogen and helium. Early in the universe's history, only hydrogen and helium existed. Everything else had to be created in stars, so older stars have lower metallicity. They formed from more primordial material. Younger stars have higher metallicity because they formed from gas that had been enriched by previous generations of stars. Bulge stars tend to have lower metallicity than the stars in the spiral arms, confirming that they're older and formed when the galaxy was young and hadn't yet produced as many heavy elements. The bulge has a different shape than the disk. While the disk is flat and extends out in a plane, the bulge is roughly spherical, or more accurately, ellipsoidal. It's somewhat flattened, but still maintains a three-dimensional structure. Stars in the bulge aren't orbiting in neat circular paths like disk stars. Their orbits are more chaotic, more elliptical, oriented in all different directions. This tells us something about how the bulge formed. There are two main theories. One is that the bulge formed early in the galaxy's history from gas that collapsed before it had a chance to settle into a rotating disk. The other is that the bulge formed through the merger of smaller galaxies early in Andromeda's life, with the stars from those merged galaxies settling into the chaotic, three-dimensional distribution we see today. Evidence suggests both processes probably played a role. Some of the bulge likely formed from primordial collapse, while other parts formed from mergers. Andromeda has been cannibalizing smaller galaxies throughout its history, and many of those consumed galaxies probably contributed their stars to the bulge. There's also evidence of a disk component within the bulge, younger stars in a flattened distribution that might represent a later generation of star formation after the main bulge had already formed. So the bulge isn't entirely homogeneous. It has structure, history, multiple components with different ages and origins. Gravitationally, the bulge dominates the inner region of Andromeda. The combined mass of all those densely packed stars creates an intense gravitational field that affects the orbits of everything nearby. Stars in the inner disk feel the bulge's gravity more than they feel the rest of the disk. Gas flowing in the inner galaxy is funneled by the bulge's gravitational influence. The bulge also serves as a reservoir of stellar mass that's effectively locked away from the ongoing processes in the disk. Those stars aren't participating in the spiral density waves. They're not in regions where new star formation is happening. They're essentially retired, orbiting peacefully in the inner galaxy, having completed their active participation in the galaxy's evolution. But they're not inactive in terms of stellar evolution. Many of these stars are becoming red giants, swelling up as they exhaust their core hydrogen. Some are shedding their outer layers, creating planetary nebulae. Others are dying and becoming white dwarfs. The bulge might look stable and unchanging on galactic timescales, but on stellar timescales, it's full of individual dramas as stars reach the end of their lives. There are also globular clusters associated with the bulge. These are ancient, tightly bound spherical collections of stars that orbit through and around the bulge region. We'll talk more about globular clusters later, but they're part of the bulge's ecosystem, adding to its complexity. Comparing to the Milky Way, our galaxy's bulge is smaller and less massive than Andromeda's, which is consistent with Andromeda being the larger galaxy overall. Our bulge also has a bar structure, which Andromeda seems to lack. This affects how gas flows in the inner galaxy and might influence star formation rates in the central regions. The central bulge of Andromeda is ancient, dense, and massive. It's the gravitational anchor of the galaxy, the core around which everything else rotates, and a fossil record of the galaxy's early history written in the properties of its stars. Now we descend to the absolute center of Andromeda, to the darkest point in the galaxy. Sitting right at the core, lurking at the heart of the bulge, is a monster. A supermassive black hole weighing between 100 and 200 million times the mass of the Sun. Let's put that in perspective immediately. Our galaxy's central black hole, Sagittarius A, weighs about 4 million solar masses. Andromeda's central black hole is 25 to 50 times more massive. It's not just bigger, it's in a completely different category of scale. If you replaced our Sun with Andromeda's black hole, the event horizon, the boundary beyond which nothing can escape, not even light, would extend beyond the orbit of Mercury, maybe even close to Venus's orbit, depending on the exact mass. It's a gravitational abyss so deep that it warps space-time around it into an inescapable well. But here's the thing about supermassive black holes. They're not actively sucking in everything around them like some kind of cosmic vacuum cleaner. They only affect objects that come very, very close. Most of the stars in Andromeda's bulge are completely safe from the black hole. They're orbiting at distances where the black hole's gravity is just one component among many in the complex gravitational environment of the galactic center. The black hole is only dangerous if you get within a few light years of it. Inside that radius, its gravity dominates. Stars passing through that region can be flung out at high speeds, or if they get close enough, torn apart by tidal forces in a spectacularly violent event called a tidal disruption event. Currently, Andromeda's central black hole is relatively quiet. It's not actively feeding on large amounts of material. There's no bright accretion disk, no jets of material screaming out at near light speed. It's just sitting there, a dormant giant at the heart of the galaxy. But it wasn't always quiet. There's evidence that Andromeda's black hole was much more active in the past, possibly as recently as a few 100 million years ago. During active periods, material falling into the black hole would form an accretion disk, a swirling disk of superheated gas spiraling inward toward the event horizon. The friction in the disk would heat the gas to millions of degrees, causing it to emit tremendous amounts of radiation across the electromagnetic spectrum. During these active periods, Andromeda would have been classified as an active galactic nucleus, or AGN. The central region would have outshone all the stars in the galaxy combined. Beams of particles and radiation would have shot out along the black hole's rotational axis, creating jets that could extend for thousands of light-years beyond the galaxy. We don't see that now, which means either the black hole has exhausted the available gas in its immediate vicinity, or the gas that's there isn't falling in at a high rate, or both. The black hole is essentially starving, waiting for its next meal. How do we even know the black hole is there if it's not currently active? We measure the motions of stars near the galactic center. Stars orbiting close to the center are moving incredibly fast, much faster than they would be if their orbits were only influenced by the distributed mass of stars in the bulge. The only explanation is that there's an enormous concentration of mass at the very center, something compact and massive enough to accelerate stars to those velocities. By tracking the orbits of these stars over time, astronomers can calculate exactly how much mass is at the center and how compact it is. The answer is always the same, somewhere between 100 and 200 million solar masses, concentrated in a region small enough that it can only be a black hole. The black hole itself is impossibly small compared to its mass. The event horizon of a 150 million solar mass black hole would have a radius of about 450 million kilometers. That sounds huge, and it is by human standards. It's about 3 times the distance from the Earth to the Sun, but in cosmic terms, it's tiny. You could fit this event horizon inside the orbit of Mars, with room to spare. And the actual singularity, the infinitely dense point at the very center where all the mass is concentrated, that's theoretically a point of zero size and infinite density, though quantum effects probably prevent true infinities in reality. We don't really know what's at the center of a black hole, because our physics breaks down at those extremes. What we do know is that supermassive black holes like this one seem to be common in galaxy centers. Almost every large galaxy we've studied has one. There appears to be a relationship between the mass of the central black hole and the mass of the surrounding bulge, suggesting that black holes and galaxies co-evolve, each influencing the growth of the other. The question of how these supermassive black holes formed is still debated. Did they start as stellar mass black holes that gradually accreted matter over billions of years? Did they form from the direct collapse of enormous gas clouds in the early universe? Did they grow primarily through mergers with other black holes when galaxies collided? Probably all of the above. Different black holes likely had different formation histories. Andromeda's black hole has probably been growing since the galaxy first formed, more than 10 billion years ago, accumulating mass through steady accretion and occasional merger events. When Andromeda and the Milky Way collide in about 4.5 billion years, their central black holes will eventually merge. It will take a long time. Black holes don't merge immediately when galaxies collide because the distance scales are so large. But eventually, after the two galaxies have fully merged and the stars have settled into a new configuration, the two black holes will spiral inward and coalesce. When they do, they'll release an enormous burst of gravitational waves, ripples in space-time itself propagating outward at the speed of light. The resulting black hole will weigh about 200,250 million solar masses, larger than either of the original black holes, and it will settle at the center of the new merged galaxy. For now, though, Andromeda's supermassive black hole sits quietly at the galactic center, a sleeping giant surrounded by millions of stars, an object so massive and so compact that it represents one of the most extreme environments in the entire universe. Here's where Andromeda gets really strange. When astronomers studied the very center of the galaxy with high-resolution instruments, they found something unexpected. The nucleus, the brightest central point of the galaxy, isn't a single point, it's double. There are two bright concentrations of light at Andromeda's core, separated by about 5 light-years. For years, this was a complete mystery. Why would the galactic center have two nuclei? What could possibly create such a structure? The first thought was that maybe Andromeda had two supermassive black holes. This wouldn't be completely crazy. When galaxies merge, they can temporarily have two central black holes that haven't yet spiraled together and merged. But closer study ruled this out. Only one of the bright points shows the characteristics of being at the absolute dynamical center of the galaxy. Only one has the orbital velocities of surrounding stars, consistent with a supermassive black hole. So if it's not two black holes, what is it? The leading explanation is both simpler and weirder. The double nucleus is probably an optical illusion created by the structure of the stellar disk around the black hole. Here's how it works. The actual black hole is at one of the bright points. We'll call it P2. This is the true center of the galaxy, the point where all the mass is concentrated, where the gravitational potential well is deepest. The other bright point, P1, is actually the peak of an elongated disk of stars orbiting the black hole. This disk isn't centered on the black hole. It's offset, eccentric, and because of the way we're viewing it from Earth, the densest part of this disk appears as a separate bright point from the black hole itself. Think of it like this. Imagine a ring of stars orbiting a black hole, but the ring isn't perfectly circular and isn't perfectly centered on the black hole. Now imagine you're viewing this ring edge-on, or nearly edge-on. The part of the ring where the stars are most densely packed, which isn't necessarily at the center, would appear as a bright concentration. Meanwhile, the black hole itself, surrounded by its own cluster of stars, would appear as a separate bright point. That's what we're seeing. P1 is the bright peak of an eccentric stellar disk. P2 is the actual black hole and the tight cluster of stars immediately around it. But this raises another question. Why is the disk eccentric? Why isn't it centered on the black hole? The most likely explanation is that Andromeda's core experienced a massive disruption sometime in the past, probably a galactic merger. When a smaller galaxy fell into Andromeda and spiraled down to the core, the interaction would have scattered stars, disrupted orbits, and potentially created this eccentric disk structure. Computer simulations support this idea. When you model a small galaxy falling into a larger galaxy and merging with its core, you can produce eccentric disk structures that look very similar to what we observe in Andromeda. This means the double nucleus is a fossil, a remnant of a violent event that happened possibly hundreds of millions of years ago. It's direct evidence that Andromeda has been cannibalizing other galaxies, eating them and incorporating their stars into its own structure. There's also evidence of other peculiarities in Andromeda's core that support the merger hypothesis. The distribution of stars isn't perfectly smooth. There are density variations, clumps, and asymmetries that suggest past disruptions. Some researchers have proposed that the merger might have happened relatively recently, cosmically speaking, maybe 200 million years ago. That's recent enough that the core hasn't fully relaxed back to a symmetric state. The stars are still settling down from the disruption, still working their way toward a more stable configuration. Over time, this eccentric structure will probably fade. Gravitational interactions and orbital evolution will gradually circularize the disk, smooth out the asymmetries, and eventually return the core to a more symmetric state. But that process takes hundreds of millions or even billions of years. For now, we're seeing Andromeda's core in a transitional state, still bearing the scars of past violence. The double nucleus is a reminder that galaxies aren't static. They're dynamic, evolving, occasionally violent systems that grow through merger and cannibalism. It's also a preview of what might happen to the Milky Way's core when Andromeda collides with us. Our central region will be disrupted. Stars will be scattered. The two supermassive black holes will sink toward the center of the merged system. The core of the new galaxy might look similarly disturbed for hundreds of millions of years before it settles down. The double nucleus mystery isn't completely solved. There are still details we don't fully understand about the structure and dynamics of Andromeda's core. But the basic picture, an eccentric disk created by a past merger, seems to be the best explanation we have. And it's a beautiful example of how something that looks strange and mysterious at first glance can actually be a window into a galaxy's history, a clue to past events that shaped the structure we see today. Deep within Andromeda's spiral arms, colossal stellar nurseries are forging new suns at a scale that challenges our comprehension. These aren't gentle cradles of creation. They're violent cosmic foundries where gravity, gas, and radiation wage war to birth the next generation of stars. The largest of these star-forming regions span hundreds of light-years across, containing enough material to create millions of stars like our Sun. Astronomers have identified thousands of these stellar nurseries scattered throughout Andromeda's disk, glowing brilliantly in infrared and ultraviolet light as newborn stars illuminate the gas clouds that spawned them. But here's where it gets truly fascinating. When we compare Andromeda's star formation rate to our own Milky Way, we discover something unexpected. Despite being larger and containing more material, Andromeda is actually forming new stars at roughly the same rate as our galaxy, about one solar mass per year. This seems counterintuitive until you understand what it reveals. Andromeda is an aging giant, past its prime of vigorous star formation, having already converted much of its available gas into stars during earlier, more active epochs. The most intense star formation occurs in Andromeda's distinctive ring structure, located about 32,000 light-years from the galactic center. This isn't a uniform process. Star formation happens in clustered bursts, creating associations of young massive stars that will live fast and die young, exploding as supernovae within mere millions of years. Some of these stellar nurseries are so massive they outshine entire dwarf galaxies, with individual regions containing star clusters of 50,000 solar masses or more, all formed within the last few million years. What makes these regions particularly remarkable is their variety. Some nurseries are creating predominantly low-mass stars, the cosmic majority that will burn steadily for trillions of years. Others are forging massive stellar monsters, blue supergiants, dozens of times more massive than our Sun, stars so luminous they could be seen from millions of light-years away. These massive stars are the engines of cosmic recycling, destined to explode and scatter heavy elements across the galaxy, enriching future generations of stars and perhaps even seeding the formation of planetary systems. The star formation regions in Andromeda also serve as cosmic laboratories, allowing astronomers to study stellar birth across a range of environments simultaneously. From the dense, metal-rich inner regions to the sparse, pristine outer arms, each nursery offers unique conditions that affect how stars form, how massive they can become, and how efficiently gas converts into stellar matter. This galactic-scale experiment is teaching us fundamental truths about star formation that we simply cannot learn from our vantage point within the Milky Way alone. Orbiting Andromeda like ancient sentinels are approximately 460 globular clusters, spherical cities of stars that have witnessed nearly the entire history of the universe. These aren't just stellar groupings, they're cosmic time capsules, each containing hundreds of thousands to millions of stars, bound together by gravity and formations so dense that near their cores, stars are packed millions of times more tightly than in our solar neighborhood. To truly grasp the scale of Andromeda's globular cluster system, consider this. If our Sun were located in the heart of one of these clusters, our night sky would be perpetually illuminated by thousands of stars brighter than Venus, creating a celestial spectacle utterly alien to our terrestrial experience. There would be no true darkness, no Milky Way visible overhead, just an overwhelming dome of stellar brilliance. Andromeda's globular cluster population significantly exceeds the Milky Way's approximately 150 to 200 clusters, and this difference tells a profound story about galactic evolution. The abundance of globular clusters suggests that Andromeda formed through more merger events, each contributed galaxy adding its own retinue of ancient clusters to Andromeda's growing collection. These clusters range in age from nearly as old as the universe itself, some exceeding 13 billion years, to relative youngsters of only a few billion years old, though even these youngsters formed when the universe was a fraction of its current age. What makes these clusters particularly valuable to astronomers is their chemical composition. The oldest globular clusters are metal-poor, formed when the universe contained almost nothing but hydrogen and helium. The younger clusters show progressively higher metallicities, documenting how successive generations of stars enriched the cosmic environment with heavier elements forged in stellar cores and scattered by supernovae. By studying Andromeda's globular clusters, we're essentially reading the periodic table of cosmic history, element by element, generation by generation. The spatial distribution of these clusters is equally revealing. They form a roughly spherical halo around Andromeda, extending far beyond the visible galactic disk, with some clusters orbiting at distances of over 300,000 light-years from the galactic center. Their orbits are highly eccentric, long, elongated paths that carry them from the outer reaches of the halo, plunging through the galactic disk and back out again. Journeys that take hundreds of millions of years to complete. These orbital patterns preserve information about the galaxy's gravitational potential and mass distribution, including the invisible dark matter halo that dominates Andromeda's total mass. But perhaps the most humbling aspect of Andromeda's globular clusters is their longevity. While civilizations rise and fall in cosmic eye blinks, while planets form and are destroyed, while entire stellar populations are born and die, these clusters persist. They have orbited Andromeda since before our solar system existed, and they will likely continue their vigil billions of years after our Sun has exhausted its fuel and faded to a cold ember. They are, in the most literal sense, ancient beyond our comprehension, survivors from a universe utterly different from the one we inhabit today. Within Andromeda's vast expanse exist individual objects so remarkable they deserve recognition as cosmic landmarks in their own right. These aren't merely interesting statistical entries in astronomical catalogues. They're extreme examples of stellar physics, pushing the boundaries of what we thought possible. Let's start with the supergiant stars, the true leviathans of Andromeda's stellar population. Among these titans, astronomers have identified blue supergiants with luminosities exceeding 500,000 times that of our Sun. If you could somehow replace our Sun with one of these monsters, its radiation would vaporize Earth instantly, and its surface would extend beyond the orbit of Mars. These stars are so intrinsically bright that despite being 2.5 million light-years away, they can be individually resolved and studied with our most powerful telescopes. Individual stars visible across the vast cosmic gulf separating our galaxies. Then there are Andromeda's massive star clusters, gravitationally bound collections of stars that dwarf anything comparable in our own galaxy. The largest of these clusters, designated NGC 206, is visible even in modest amateur telescopes as a distinct patch of light within Andromeda's spiral arms. This single cluster contains thousands of young, hot stars with a combined mass exceeding 100,000 times that of our Sun, all formed within the last 10 million years. Yesterday, in cosmic terms. The cluster shines so brightly it would cast visible shadows on a planet orbiting within it, and its collective stellar winds create cavities in the surrounding interstellar medium spanning hundreds of light-years. Perhaps even more impressive are the giant molecular clouds, the reservoirs of raw material from which future stars will form. The largest of these clouds in Andromeda contain millions of solar masses worth of hydrogen, helium, and trace amounts of heavier elements, all maintained at temperatures just a few dozen degrees above absolute zero. These aren't diffuse wisps. They're dense cosmic structures where the gas reaches concentrations of thousands to millions of particles per cubic centimeter, still an excellent vacuum by Earth standards, but incredibly dense by interstellar norms. Within these clouds, gravity is slowly winning its eternal battle against thermal pressure and magnetic fields, gathering material together, setting the stage for the birth of stars that won't ignite for another million years. Among the most intriguing individual objects are Andromeda's supernova remnants, the expanding shells of debris from stars that exploded thousands of years ago. Some of these remnants span over 300 light-years across, and are still expanding at speeds of thousands of kilometers per second, plowing into the surrounding interstellar medium and triggering new waves of star formation through their passage. Each remnant tells the story of a stellar death, some from massive stars that exhausted their nuclear fuel, others from white dwarfs that accumulated too much mass from companion stars and detonated in thermonuclear explosions of staggering violence. And let's not forget the HII regions, vast volumes of ionized hydrogen gas surrounding young, massive stars. The largest of these regions in Andromeda span over 1,000 light-years and glow with the characteristic red light of hydrogen emission, visible in deep photographs as pink and red patches scattered throughout the galactic disk. These regions are cosmic recycling centers where stellar winds and radiation from newborn stars are dispersing and ionizing the very clouds from which they formed, returning material to the interstellar medium and enriching it with the heavy elements forged within stellar cores. What makes these individual objects particularly valuable is that they provide ground truth for our theoretical models. We can calculate what a star of a certain mass should look like, how bright it should be, how it should evolve, and then we can point our telescopes at Andromeda and actually see such stars, testing our predictions against cosmic reality. Every observation refines our understanding, every measurement constrains our models, and every discovery reminds us that the universe is always stranger and more magnificent than our theories predict. Andromeda doesn't rule the local group alone. Surrounding this galactic titan is a retinue of at least 14 confirmed dwarf satellite galaxies, with potentially dozens more awaiting discovery in the outer reaches of Andromeda's gravitational domain. These aren't merely cosmic ornaments, they're complete galaxies in their own right, each containing millions to billions of stars, each with its own history of star formation, its own dark matter halo, its own story of survival or consumption by their massive host. The two most prominent members of this satellite family are M32 and M110, both visible in the same telescopic field of view as Andromeda itself, and catalogued by Charles Messier in the 18th century. But beyond these famous companions lie a diverse collection of dwarf galaxies spanning a range of types: dwarf spheroidals, dwarf ellipticals, dwarf irregulars, each representing different evolutionary pathways and different responses to the gravitational tyranny of their massive host. When we compare Andromeda's satellite system to the Milky Way's, we find both similarities and intriguing differences. Both galaxies have comparable numbers of known satellites, though deep surveys continue to discover new, extremely faint dwarfs around both systems. The Milky Way's satellites include famous systems like the Large and Small Magellanic Clouds, which are substantially more massive than any of Andromeda's known companions. This difference may simply reflect observational bias. We can detect fainter satellites around the Milky Way because they're so much closer, or it may represent a genuine difference in satellite populations that could tell us something profound about how these two galaxies assembled their retinues. What's particularly fascinating is the spatial distribution of Andromeda's satellites. Rather than being randomly scattered around their host, many of them appear to be arranged in a vast, flattened structure known as the Great Plain of Andromeda, a disk-like configuration of satellite galaxies that extends across hundreds of thousands of light-years. This plane is rotating, with satellites on one side approaching us and those on the opposite side receding, suggesting this isn't a random alignment but a coherent structure. The existence of such planes around both Andromeda and the Milky Way poses significant challenges for our standard cosmological models, which predict satellite distributions should be roughly spherical. The satellite galaxies themselves range from relative giants like M32, containing hundreds of millions of stars, down to ultra-faint dwarfs that contain fewer stars than some globular clusters, small dark matter-dominated systems that produce so little light they're almost invisible, detectable only through painstaking searches that identify overdensities of stars against the background. These ultra-faint dwarfs are particularly valuable for cosmology because their dynamics are dominated by dark matter, making them excellent laboratories for studying this mysterious component that constitutes 85% of the universe's matter. But perhaps the most sobering aspect of Andromeda's satellite system is its future, or rather, the lack thereof for many of these galaxies. Orbital dynamics suggest that several of Andromeda's satellites are on eventual collision courses with their host, destined to be tidally disrupted and absorbed, their stars scattered into Andromeda's halo, their dark matter halos merged with Andromeda's own. This isn't speculation. We can see evidence of this process happening now, with tidal streams of stars stripped from disrupting satellites, tracing out the orbital paths of galaxies that no longer exist as coherent structures. The satellite galaxies we observe today are the survivors, for now, of a brutal process of galactic cannibalism that has been ongoing for billions of years and will continue for billions more. Among all of Andromeda's satellites, M32 stands out as one of the most peculiar objects in the entire local group. This isn't merely another dwarf galaxy orbiting its massive host. It's an astrophysical enigma, a galaxy that shouldn't exist in its current form, and one that has fundamentally challenged our understanding of how galaxies evolve. At first glance, M32 appears unremarkable, a compact elliptical galaxy containing a few 100 million stars orbiting just 24,000 light-years from Andromeda's center, so close it appears to be sitting directly on top of the larger galaxy's disk when viewed from Earth. But when astronomers began studying M32 in detail, they discovered something shocking. This galaxy is one of the densest stellar systems in the local universe, with stars packed together at concentrations that exceed those found in the cores of even the most massive elliptical galaxies. The most widely accepted explanation for M32's bizarre properties is that we're looking at the stripped core of what was once a much larger galaxy. Billions of years ago, this galaxy likely resembled a small spiral or elliptical system containing tens of billions of stars. But as it orbited Andromeda, tidal forces, the same forces that create ocean tides on Earth but operating on galactic scales, began tearing away the outer layers of the smaller galaxy, stripping stars from its outskirts and adding them to Andromeda's halo and disk. What remains is M32, the ultra-dense core, the gravitational heart of a galaxy that has been literally flayed by its massive companion. Evidence for this stripping scenario comes from multiple sources. First, M32's stellar population is unusually rich in heavy elements, more so than would be expected for a galaxy of its current mass. This makes sense if M32 is the remnant of a larger system that underwent extensive star formation, enriching its interstellar medium with elements forged in stellar cores before that material was stripped away. Second, astronomers have identified faint tidal streams of stars extending from M32 and wrapping around Andromeda, the stellar debris of the stripping process, smoking gun evidence of galactic cannibalism caught in the act. But M32 holds even deeper mysteries. At its center lurks a supermassive black hole of approximately 2.5 million solar masses, not particularly large by the standards of galaxy core black holes, but surprisingly massive for a galaxy of M32's current size. This black hole mass is another clue that M32 was once substantially larger, as black hole masses typically scale with the total mass of their host galaxy's bulge. The black hole grew during M32's earlier, more massive incarnation, and like the dense stellar core, it survived the tidal stripping that removed the galaxy's outer envelope. What makes M32 particularly valuable scientifically is that it represents a different pathway of galaxy evolution than we typically observe. Most satellite galaxies are eventually completely disrupted, their stars scattered into their host's halo, with no coherent remnant surviving. M32 shows us an intermediate stage, a galaxy being consumed, but slowly enough that its core remains intact, at least for now. By studying M32, we can understand the physics of tidal stripping, how galaxies lose mass to their hosts, and what structures can survive the brutal environment of close-in satellite orbits. The future of M32 is unfortunately sealed. Orbital calculations suggest that it will continue to lose mass to tidal stripping, gradually diminishing over the next several billion years. Eventually, perhaps in another 5 billion years, it may be completely disrupted, its remaining stars scattered into Andromeda's halo, its central black hole sinking to merge with Andromeda's own supermassive black hole. M32 is a galaxy in its death throes, and we're privileged, in a cosmic sense, to witness this slow-motion galactic execution, learning from its demise how small galaxies are absorbed by their larger companions. M1110 presents a different kind of puzzle than its compact companion M32. This dwarf elliptical galaxy, also visible in the same telescopic view as Andromeda, appears at first to be a textbook example of its type, a smooth, featureless collection of stars with no obvious structure, no spiral arms, no active star formation. Elliptical galaxies, the theory goes, are stellar graveyards, systems that exhausted their gas reserves billions of years ago and now contain only old red stars slowly aging toward their eventual deaths. Except M110 doesn't follow the rules. When astronomers examined it closely with advanced instruments, they discovered something that shouldn't exist in an elliptical galaxy. Young blue star clusters scattered throughout its structure, some containing stars less than 100 million years old. This is the astronomical equivalent of finding a modern smartphone in a pharaoh's tomb. These objects simply shouldn't be there according to our standard model of how elliptical galaxies evolve. The presence of young stars in M110 tells us that this galaxy has experienced relatively recent episodes of star formation, events that occurred within the last few 100 million years, recent in cosmic terms. But where did the gas come from to form these stars? Elliptical galaxies are supposed to be gas-poor, having either converted all their gas into stars or lost it through various processes billions of years ago. The most likely explanation is that M110 has managed to retain or reaccumulate small amounts of gas, perhaps from the slow death of older stars which shed their outer envelopes in their final stages, or possibly from gas stripped from the outer reaches of Andromeda itself during close passages. This discovery has profound implications for our understanding of galaxy evolution. It suggests that the classification of galaxies into rigid types, spirals, ellipticals, irregulars, is oversimplified, and that galaxies can continue to evolve and change even after they've supposedly settled into their final form. M110 demonstrates that elliptical galaxies aren't necessarily dead. They're just mostly dormant, capable of brief episodes of renewed activity under the right conditions. M110 also shows evidence of complex internal structure that contradicts the smooth, featureless appearance suggested by early observations. Modern imaging reveals subtle shells and ripples in its stellar distribution, signatures of past interactions or mergers with even smaller systems. These features are like archaeological layers in sedimentary rock, preserving information about events that occurred hundreds of millions to billions of years ago, allowing us to reconstruct M110's turbulent history. The galaxy's relationship with Andromeda adds another layer of complexity. M110 orbits at a distance of approximately 200,000 light-years from Andromeda's center, far enough that tidal stripping hasn't yet devastated its structure the way it has with M32, but close enough that Andromeda's gravitational influence is definitely felt. During its closest approaches to Andromeda, gravitational compression may actually trigger bursts of star formation in M110 by compressing what little gas the dwarf galaxy retains, forcing it to collapse and form new stars. This interaction-driven star formation could explain the young stellar populations. M110's proximity to its massive host isn't just destroying it, it's periodically rejuvenating it. What makes M110 particularly valuable for astronomers is that it serves as a laboratory for studying star formation in low-mass, low-metallicity environments. The stars forming in M110 today are doing so in conditions radically different from those in large spiral galaxies like the Milky Way or Andromeda. The gas in M110 is metal-poor compared to our own galaxy, more closely resembling the primordial composition of the early universe. By studying star formation in M110, we can test our theories about how stars formed in the early universe, when the cosmic environment was similarly pristine. The ultimate fate of M110, like M32, is likely absorption by Andromeda. Orbital modeling suggests that over the next several billion years, M110 will be slowly tidally disrupted, its stars scattered into Andromeda's vast halo. The young star clusters we observe today will become globular clusters, orbiting Andromeda, their origin in M110 obscured by billions of years of orbital evolution. Future astronomers studying Andromeda, billions of years from now, may puzzle over these clusters, wondering where they came from, never knowing they're witnessing the last remnants of a dwarf galaxy that briefly defied expectations before being consumed by its massive companion. Beyond Andromeda's bright spiral arms, beyond the disk of stars visible in even powerful telescopes, extends something truly vast, a diffuse stellar halo that reaches outward for over 1 million light-years in all directions, creating a ghostly sphere of stars that dwarfs the visible galaxy. This isn't just empty space with a few scattered stars. It's a massive structural component of the galaxy, containing billions of stars and representing a significant fraction of Andromeda's total stellar mass. To understand the scale of this halo, consider that it extends roughly halfway to the Milky Way. If we could see this structure with our naked eyes, Andromeda wouldn't appear as a small, fuzzy patch in the sky. It would span an area dozens of times larger than the full moon, a vast faint dome of stars covering a significant portion of our celestial sphere. But because these halo stars are so dispersed and individually faint, the structure remains invisible to the unaided eye, and even to most telescopes, detectable only through careful surveys that painstakingly identify and map individual stars across enormous areas of sky. The stellar halo isn't uniform. It's filled with structure, streams, shells, and overdensities that trace out the orbital paths of satellite galaxies that have been tidally disrupted and consumed by Andromeda over billions of years. These features are like fossil records preserved in starlight, allowing astronomers to reconstruct Andromeda's violent history of galactic cannibalism. Each stream represents a satellite galaxy that once orbited Andromeda as an independent system, but was eventually torn apart by tidal forces, its stars scattered along its former orbit to create the stream we observe today. The stars in the halo are predominantly old, ancient red giants and faint dwarf stars that formed in the early universe, many exceeding 10 billion years in age. These aren't stars born in Andromeda's disk. They're immigrants, stars that formed in smaller galaxies that were subsequently destroyed and incorporated into Andromeda's structure. Their chemical compositions reveal their origins. Many are metal-poor compared to disk stars, having formed in smaller, less evolved systems where fewer generations of stars had lived and died to enrich the interstellar medium with heavy elements. What makes the halo particularly significant is what it tells us about how large galaxies grow. The presence of all these disrupted satellite remnants demonstrates that Andromeda, and by extension all large galaxies, grows through a process called hierarchical assembly. Galaxies don't form as single monolithic structures. They build up over billions of years through the accretion and merger of smaller systems. Every star in Andromeda's halo was once part of a separate galaxy, each with its own history, its own population of stars, its own dark matter halo. Those galaxies no longer exist as independent entities, but their stars survive, now orbiting as part of Andromeda's vast halo, ghostly monuments to galaxies long dead. The halo also contains a significant population of globular clusters, those ancient, spherical collections of stars we discussed earlier. Many of these clusters may have originally orbited the satellite galaxies that were consumed by Andromeda, and now orbit the larger galaxy at enormous distances, some well beyond 300,000 light-years from Andromeda's center. These clusters serve as tracers of the galaxy's total mass, including its dark matter halo. By measuring the velocities of these distant clusters, astronomers can map out Andromeda's gravitational field and infer the distribution of dark matter, the invisible component that dominates the galaxy's total mass. Recent observations have revealed that Andromeda's halo extends even farther than previously thought, with individual halo stars detected at distances exceeding 500,000 light-years from the galactic center. At these extreme distances, the boundary between what belongs to Andromeda and what belongs to the intergalactic medium becomes increasingly fuzzy. These outermost halo stars are barely bound to Andromeda, orbiting in the weak gravitational field of the galaxy's extended dark matter halo, taking hundreds of millions to billions of years to complete a single orbit. The stellar halo is also a laboratory for studying dark matter. The motions of halo stars are determined primarily by the gravitational potential of the dark matter halo, rather than by the visible stars and gas, making them excellent tracers of dark matter distribution. By mapping how fast halo stars move at different distances from Andromeda's center, astronomers can infer the shape and extent of the dark matter halo, testing models of how dark matter is distributed within galaxies. These observations have revealed that Andromeda's dark matter halo likely extends to distances of 1–2 million light-years, far beyond even the extended stellar halo, creating a gravitational sphere of influence that encompasses much of the local group. Andromeda is a serial killer. Over its 10 billion-year history, it has consumed dozens, perhaps hundreds, of smaller galaxies, tearing them apart and incorporating their stars into its own structure. This isn't speculation or dramatic exaggeration. It's observable fact, written in the sky in stellar streams and disrupted satellites, a cosmic crime scene so well preserved that astronomers can reconstruct these ancient murders with remarkable detail. The most dramatic evidence comes from the stellar streams threading through Andromeda's halo. These aren't diffuse, random distributions of stars. They're coherent structures, narrow bands of stars tracing out specific orbital paths around the galaxy. When a satellite galaxy orbits a larger host, tidal forces stretch it along its orbit, pulling stars from the front and back of the satellite and creating two tidal tails, one leading the satellite in its orbit, one trailing behind. As the satellite continues to orbit and lose mass, these tails wrap around the host galaxy multiple times, creating the streams we observe. Each stream is essentially a dissected galaxy, its stars spread along hundreds of thousands of light-years, but all sharing a common origin and orbital history. The giant stellar stream, discovered in 2001, is the most prominent of these structures, a vast arc of stars extending across Andromeda's disk and halo, containing millions of individual stars all moving together through space. This stream represents the tidal debris from a galaxy that was probably similar in mass to the Small Magellanic Cloud, a significant galaxy in its own right, one that would have contained billions of stars, destroyed sometime within the last few billion years. The stream wraps around Andromeda multiple times, with different segments representing different orbital phases of the disruption process. By modeling the dynamics of this stream, astronomers have reconstructed the orbit of the progenitor galaxy, determining when and how it was destroyed and what its properties were before Andromeda tore it apart. But the giant stellar stream is just one of many such structures. Surveys of Andromeda's halo have identified dozens of streams, shells, and overdensities, each representing a separate accretion event, a separate galaxy consumed by Andromeda's gravitational maw. Some of these are relatively recent, structures that are still coherent and easily traceable. Others are ancient and partially dispersed, their stars gradually mixing into the general halo population, but still retaining subtle correlations in their positions and velocities that reveal their common origin. The most recent victim we can observe in the act of being consumed is the Triangulum Galaxy M33, though whether it's a satellite of Andromeda or the Milky Way, or gravitationally bound to both, remains debated. Regardless, tidal interactions are already affecting M33's structure, pulling stars from its outer regions and potentially altering its orbit in ways that may eventually lead to its complete disruption. What makes this galactic cannibalism particularly interesting is that it's not a past process that ended long ago. It's ongoing. Andromeda is actively consuming several of its current satellite galaxies, with tidal streams visible extending from systems like NGC 147 and NGC 185. These galaxies are being eaten in real time, cosmic timescales being what they are, losing mass with each orbit and facing eventual complete destruction. The remnants of these consumed galaxies aren't just scattered randomly into Andromeda's halo. The orbital dynamics of the disruption process create distinctive patterns. Shells, for instance, which are faint, arc-shaped overdensities created when stars from a disrupted satellite reach the apocenter farthest point of their orbit simultaneously, briefly increasing the stellar density in that region before continuing their orbital journey. By mapping these shells and their positions, astronomers can work backwards to determine the properties of the progenitor galaxy and the dynamics of the merger that destroyed it. Chemical analysis of halo stars provides additional evidence for this cannibalistic history. Stars born in smaller galaxies have different chemical compositions than stars born in large galaxies like Andromeda. Small galaxies experience less efficient star formation and fewer supernovae per unit mass, resulting in different ratios of chemical elements. By measuring the chemical compositions of halo stars, Astronomers can identify which stars likely formed in Andromeda's disk and which were acquired through mergers, essentially performing a cosmic autopsy to determine the galaxy's diet. The dark matter halos of consumed satellites also leave their mark, though they're far harder to observe directly. When a satellite galaxy is tidally disrupted, its stars are stripped away relatively quickly, but its dark matter halo is more diffuse and less susceptible to tidal disruption. These dark matter halos may survive long after the stellar component has been destroyed, creating substructures within Andromeda's overall dark matter halo, invisible scaffolding, that gravitationally influences the motion of stars and gas, but produces no light of its own. Andromeda is coming for us. Right now, at this very moment, the entire Andromeda Galaxy is hurtling through space directly toward the Milky Way at a velocity of 110 kilometers per second. That's approximately 250,000 miles per hour, or about 0.037% the speed of light. To put this in more familiar terms, that's roughly 300 times faster than a rifle bullet, fast enough to cross the United States in less than 15 seconds, if such a trajectory were possible. But cosmic scales require cosmic measurements, so let's translate this velocity into more appropriate units. At 110 kilometers per second, Andromeda is approaching at roughly 3.47 billion kilometers per year. A light year is approximately 9.46 trillion kilometers, which means Andromeda closes the distance by about 366 light years every million years. The current separation between the Milky Way and Andromeda is approximately 2.5 million light-years. So simple arithmetic suggests, well, we'll get to that calculation in the next section. What makes this approach velocity particularly remarkable is that it's measured against the general expansion of the universe. Almost everything in the observable universe is moving away from us due to the expansion of space itself, the famous cosmological redshift discovered by Edwin Hubble. But Andromeda shows a blue shift, indicating motion toward us. This happens because on local scales, distances of a few million light-years, gravity overpowers cosmic expansion. Andromeda and the Milky Way are bound together by their mutual gravitational attraction, along with the gravitational influence of the other local group members, creating an island of collapse in an otherwise expanding universe. The velocity we measure, 110 kilometers per second, is the radial velocity, the component of motion directly toward or away from us along our line of sight. But galaxies don't necessarily move in perfectly straight lines. Andromeda also has a tangential velocity, motion perpendicular to our line of sight, which is much harder to measure because it doesn't produce Doppler shifts in the spectrum. Determining this tangential motion requires measuring Andromeda's position with extraordinary precision over many years to detect its apparent motion across the sky. A motion so small it would take centuries of observations to definitively measure. Recent observations using the Hubble Space Telescope and Gaia satellite have attempted to measure this tangential motion, and the results suggest it's quite small. Andromeda's motion is predominantly radial, meaning it's moving almost directly toward us rather than past us. This is significant because it confirms that a direct collision is inevitable. If Andromeda had substantial tangential velocity, there might have been a possibility of a near miss rather than a direct impact. The approach velocity hasn't been constant over Andromeda's history, and it won't remain constant in the future. When Andromeda and the Milky Way were more distant in the past, their mutual gravitational attraction was weaker, and they were moving toward each other more slowly. As they've approached over billions of years, gravity has accelerated them, increasing the closing velocity. This acceleration will continue as the galaxies approach, with the velocity increasing dramatically during the final 100 million years before collision, as the galaxies fall into each other's increasingly dominant gravitational fields. Understanding this velocity and the approach trajectory is crucial for modeling what will happen during the collision. The speed of approach determines the energy of the impact, which influences how the galaxies will interact, whether they'll merge smoothly or experience a more violent collision with extensive tidal disruption. The angle of approach determines the geometry of the collision. whether it will be head-on or more glancing, which affects how the galactic disks will interact and what structures will survive the merger. It's worth emphasizing the sheer scale of what we're discussing. An entire galaxy, 2.5 million light-years away, containing 1 trillion stars, with a total mass of approximately 1.5 trillion suns, is moving toward us at speeds that would be considered impossibly fast by terrestrial standards. And yet, despite this enormous velocity, the distance is so vast that the collision will still take billions of years to occur. This is the fundamental paradox of cosmic scales, motion that is simultaneously incredibly fast by human standards and glacially slow by cosmological ones, requiring billions of years for processes to unfold that involve velocities that would seem instantaneous on human scales. The collision between Andromeda and the Milky Way will begin in approximately 4.5 billion years. But that single statement barely captures the epochal nature of what will unfold. A cosmic cataclysm that will play out over billions of years, transforming two majestic spiral galaxies into a single elliptical behemoth, fundamentally reshaping the local group and creating night skies that would be utterly unrecognizable to anyone who lived on Earth today. Let's walk through what an observer on Earth, or more accurately, on whatever celestial body occupies Earth's current position, as Earth itself may not survive this timeline, would witness as this collision unfolds. Today, Andromeda appears as a faint fuzzy patch in our night sky, spanning about 3 degrees, 6 times the diameter of the full moon, though only the bright central region is visible to the naked eye. Fast forward 2 billion years from now, and Andromeda will have noticeably grown, spanning perhaps 5-6 degrees, bright enough that its spiral structure might be dimly visible to dark-adapted eyes under pristine skies. The galaxy is approaching, the distance closing, but the night sky still appears relatively normal, dominated by the Milky Way's familiar band across the heavens. At 3.75 billion years from now, the transformation becomes undeniable. Andromeda now spans 1520 degrees across the sky, dominating the autumn constellation of Andromeda and extending into adjacent constellations. Its spiral arms are clearly visible, and the galaxy blazes with the light of nearly 1 trillion suns compressed into a structure spanning more than 1/3 of the distance from horizon to zenith. The increased tidal interactions are beginning to distort both galaxies, pulling tidal tails of stars from their outer regions. New waves of star formation are igniting in the compressed gas, where the galaxy's halos are beginning to overlap, creating brilliant blue knots of young star clusters visible even at this great distance. At 4 billion years, Andromeda fills 1/4 of the visible sky, a spectacular sight that would make our current Milky Way appear modest by comparison. But the view is no longer peaceful. Tidal disruption is in full swing. Both galaxies are being gravitationally contorted, their elegant spiral structures warping and distorting as they fall into each other's gravitational wells. Streams of stars are being pulled from both systems, creating vast, luminous bridges between the galaxies. Star formation has intensified dramatically, with collision-induced bursts creating new stellar populations at rates 10 times higher than either galaxy experienced independently. The night sky blazes with supergiant stars and supernova explosions from this accelerated stellar evolution. At 4.5 billion years, first contact occurs. The outermost regions of the galactic halos interpenetrate, though the disk collision is still hundreds of millions of years away. This is not a gentle merger. The orbital velocities mean the galaxies will pass through each other initially, rather than immediately coalescing. Andromeda fills half the sky, its spiral arms now torn and fragmented, no longer the majestic structure visible in our current epoch, but a galaxy in the throes of catastrophic transformation. The Milky Way's disk, seen from Earth's position, is similarly distorted, warped into an S-shape by Andromeda's gravitational pull. At approximately 5 billion years, the galactic cores pass within 50,000 light-years of each other during the first passage, The gravitational chaos is extraordinary. Star clusters are flung across hundreds of thousands of light years, tidal tails extend across millions of light years, and the combined system looks nothing like two separate galaxies anymore. Our Sun, if it's still on the main sequence, it may be transitioning to a red giant around this time, will have its orbit significantly altered, potentially being flung into the outer regions of the merger system, or possibly even ejected entirely to become an intergalactic wanderer. But the first passage isn't the end, it's just the beginning. The galaxies don't stick together on the first encounter. Instead, they pass through each other, separated again by gravity, then begin falling back together for a second collision about 1 billion years after the first passage. This second collision is typically more destructive than the first, because the galaxies have already been tidally disrupted and are approaching from different angles than the initial encounter. By 6 billion years from now, after multiple passages and gravitational interactions, the two galaxies will have thoroughly merged, their individual identities lost in a single massive elliptical galaxy that astronomers have named Milkomeda, or sometimes Milkdromeda. The beautiful spiral structures that characterized both progenitor galaxies will be completely destroyed, replaced by a smooth, featureless, elliptical distribution of stars. The combined galaxy will contain nearly 2 trillion stars, making it one of the largest galaxies in the local group, dominating the remaining dwarf galaxies that survived the merger. From Earth, or from whatever location in the merged system contains our Sun, the view would be radically different from anything we see today. The Milky Way band would be gone, replaced by a relatively uniform distribution of stars across the sky. The sky would be brighter with stars, as the central regions of the elliptical galaxy are more densely populated than the spiral arms of the Milky Way. But paradoxically, there might be fewer prominent individual stars visible, as our Sun's position in the merged galaxy would likely be farther from the galactic center than its current location in the Milky Way. It's worth pausing here to consider the human element, or rather, the absence of it. Life on Earth will almost certainly not witness this collision. Our Sun will begin its transition to a red giant in about 5 billion years, expanding to perhaps 100 times its current radius, and rendering Earth uninhabitable, if not outright consuming it, well before the galaxy merger completes. Any observers of this cosmic spectacle will not be humans as we exist today, not residing on Earth as it exists today, and quite possibly will not exist at all if complex life hasn't emerged elsewhere in the galaxy or if our descendants haven't colonized other star systems by then. But whether or not anyone is there to watch, the collision will occur. The laws of physics that govern gravity and motion don't require an audience. Two of the largest galaxies in the local group will merge, creating a structure that will persist for hundreds of billions of years, long after our Sun has exhausted its fuel and faded to a cold white dwarf, long after any memory of human civilization has been erased from the cosmos. And here's the beautiful cosmic irony. Despite the violence of this galactic collision, despite the catastrophic distortion of two magnificent spiral galaxies, individual stellar collisions will be extraordinarily rare. Stars are so far apart relative to their sizes that even when two galaxies interpenetrate, the probability of any two stars actually hitting each other is vanishingly small. This is a collision of gravity and dark matter, not of stars themselves. The galaxies will merge, but the stars will simply pass through each other like two swarms of bees occupying the same space, rearranging their orbits according to the new gravitational configuration, but rarely making physical contact. The collision between Andromeda and the Milky Way has been simulated thousands of times by supercomputers running the most sophisticated gravitational dynamics codes ever created. These aren't simple animations. They're detailed physics calculations tracking the motions of billions of particles, representing stars, dark matter, and gas clouds, evolved forward in time according to Newton's and Einstein's laws of gravity. What these simulations reveal is a cosmic dance of staggering complexity, a gravitational ballet that will unfold over 5 billion years and fundamentally transform both participants. The simulations begin with the current state: two massive spiral galaxies separated by 2.5 million light-years, approaching at 110 kilometers per second, each embedded in an enormous dark matter halo, extending far beyond their visible boundaries. The computers calculate the gravitational force between every particle and every other particle, a computational challenge requiring millions of processor hours, even with modern approximation techniques. Then advance the system forward in time steps of typically 1 million years or so, updating positions and velocities according to the gravitational forces at each step. What emerges from these calculations is remarkably consistent across different simulation codes and initial conditions. The first close passage occurs approximately 4.5 billion years from now, with the galactic centers approaching to within 50,000 to 100,000 light-years of each other, closer than the distance from our Sun to the Milky Way's center. But this isn't a gentle approach. Both galaxies are already being tidally distorted well before this first passage, with their outer regions being pulled toward each other by gravitational tidal forces. The beautiful spiral structures become warped and asymmetric, with one or two spiral arms pulled outward toward the approaching galaxy, while others are compressed inward. As the galaxies interpenetrate during the first passage, the simulations show spectacular tidal tail formation. Material from the outer regions of both galaxies is flung outward by gravitational slingshot effects, creating luminous streamers of stars and gas, extending hundreds of thousands of light-years into intergalactic space. These tails are gravitationally focused. They're not random scatterings of stars, but coherent structures tracing specific orbital trajectories determined by the precise geometry of the encounter. Some simulations show tidal tails extending over 1 million light-years, visible as thin, curved filaments if observed from outside the local group. But here's what makes the dynamics particularly complex. The galaxies don't merge on the first pass. They're moving too fast, carrying too much orbital energy to stick together immediately. Instead, after passing through each other, they separate again, moving apart to distances of perhaps 200,000 to 300,000 light-years before their mutual gravitational attraction halts the separation and pulls them back together for a second collision. This second passage, occurring roughly 1 billion years after the first, is typically more destructive than the initial encounter. The galaxies approach from different angles than the first collision, and both have already been significantly disrupted by the tidal effects of the first passage. Their spiral structures are now completely destroyed, replaced by chaotic, irregular distributions of stars and gas. The simulations show that during this second passage, the galactic cores approach even closer than during the first encounter, sometimes to within 20,000 to 30,000 light-years. After the second passage, the galaxies again separate, but this time they don't move as far apart before falling back together. The repeated passages dissipate orbital energy through a process called dynamical friction. Essentially, as the galaxies pass through each other, gravitational interactions between individual stars and dark matter particles gradually slow the relative motion of the galactic centers. Think of it as cosmic brakes applied by billions of gravitational tugs, each individually tiny, but collectively powerful enough to eventually stop the separation and bring the galaxies together. Subsequent passages occur at shorter intervals with decreasing separation distances. The third passage might occur only 500 million years after the second, with the cores approaching to within 10,000 light-years. By the fourth or fifth passage, the separation between encounters is measured in hundreds of millions rather than billions of years, and the galactic cores are close enough that they no longer separate significantly between encounters. Throughout this multi-billion-year process, the simulations track what happens to individual stellar orbits. Stars that originally orbited in the thin, orderly disks of both spiral galaxies are flung onto highly elliptical, randomly oriented orbits. The organized rotation that characterized the spiral galaxies is transformed into random motion. Stars moving in all directions rather than the coherent rotation pattern of a spiral disk. This randomization of orbits is why the final merger product is an elliptical galaxy rather than a larger spiral. The ordered motion necessary to maintain spiral structure is destroyed by the gravitational chaos of the merger. The dark matter halos also merge, but their evolution is smoother than the visible galaxies, because dark matter doesn't collide or interact except through gravity. The dark matter from both galaxies simply interpenetrates and relaxes into a single larger halo that will eventually achieve an equilibrium configuration, probably a roughly spherical or slightly ellipsoidal distribution extending 1 to 2 million light-years from the merged galactic center. One of the most fascinating aspects revealed by simulations is the fate of the supermassive black holes at the centers of both galaxies. After the galaxies merge, both black holes, Sagittarius A from the Milky Way and Andromeda's central black hole, will be embedded in the merged galaxy. Dynamical friction gradually causes them to spiral toward the center of the merged system, shedding orbital energy through gravitational interactions with surrounding stars. Eventually, perhaps a few 100 million years after the final merger, the two black holes will themselves merge in a catastrophic event that will release more energy in gravitational waves in a few seconds than the Sun will emit in electromagnetic radiation over its entire lifetime. The simulations also reveal enormous variations depending on the precise details of the initial conditions. The angle of approach matters tremendously. A head-on collision produces different results than a more glancing encounter. The spin orientations of the galaxies matter. Whether the disks are aligned or counter-rotating affects how efficiently angular momentum is transferred and dissipated. Even small differences in the exact masses of the galaxies or the structure of their dark matter halos can produce significantly different evolutionary tracks. Modern simulations have become sophisticated enough to track not just the dark matter and stars, but also the gas, including the complex physics of heating, cooling, star formation, and stellar feedback. These simulations show that gas clouds collide during the merger much more violently than the collisionless stars and dark matter. When gas clouds from both galaxies smash into each other at hundreds of kilometers per second, the kinetic energy is converted to thermal energy, heating the gas to millions of degrees. This heated gas emits X-rays and can be observed in real merging galaxies, providing observational confirmation of the simulation predictions. But not all the gas is heated to these extreme temperatures. In regions where the compression is strong but the shock velocities are lower, the gas is compressed and cooled rather than heated, triggering massive bursts of star formation. The simulations predict that during the most active phases of the merger, star formation rates will spike to 10 or even 100 times the current rates in either galaxy, creating brilliant starbursts visible across millions of light-years. These starbursts will produce tens of millions of new stars in concentrated regions, creating superstar clusters that will eventually evolve into globular clusters in the merged galaxy. The computational power required for these simulations is staggering. A high-resolution simulation tracking billions of particles at time steps fine enough to resolve important dynamical processes might require months of runtime on supercomputers with thousands of processors working in parallel. And even these simulations are approximations. They can't track every star individually. There simply isn't enough computing power in the world. So they use statistical methods and representative particles, each representing hundreds of thousands or millions of actual stars. Despite their limitations, these simulations have been remarkably successful at predicting what we observe in real galaxy mergers throughout the universe. When astronomers find galaxies in various stages of merging, the structures they observe, the tidal tails, the distorted spiral arms, the starbursts, the distribution of stars and gas, match simulation predictions with impressive fidelity. This gives us confidence that the simulations are capturing the essential physics, even if they can't reproduce every detail. After 5 billion years of gravitational violence, After multiple passages and countless stellar orbits violently rearranged, the merger will be complete. What emerges from this cosmic crucible will be something entirely new, a massive elliptical galaxy that astronomers have nicknamed Milkomeda, though Milkdromeda is also used, blending the names of its progenitor galaxies into a single word that represents their irreversibly merged future. Milkomeda will be a galactic giant, containing approximately 2 trillion stars, the combined stellar populations of both parent galaxies, minus whatever was lost to tidal ejection during the merger process. Some simulations suggest that 5.10% of stars from both galaxies will be flung into intergalactic space during the merger, becoming orphaned stars wandering the local group with no galaxy to call home. But even accounting for these losses, Milkomeda will be one of the most massive galaxies in the local group, dramatically outmassing any of the remaining dwarf galaxies that survived the merger chaos. The shape of Milkomeda will be fundamentally different from either of its spiral progenitors. Instead of the flat, rotating disks that characterize the Milky Way and Andromeda, Milkomeda will be roughly spheroidal or ellipsoidal. Imagine a three-dimensional football or rugby ball rather than a frisbee. The galaxy will be much thicker than either parent galaxy's disk, extending tens of thousands of light-years in all directions from its center, rather than being compressed into a thin plane just a few thousand light-years thick. This transformation in shape reflects a fundamental change in the orbital dynamics of the stars. In a spiral galaxy, most stars orbit in roughly the same direction, in approximately circular paths within the galactic plane, like cars on a racetrack. But in Milkomeda, stellar orbits will be highly elliptical and randomly oriented, some stars diving close to the galactic center before swinging out to the periphery, others on plunging orbits that take them through the densest central regions, still others on gentler paths that keep them in the outer regions. The net rotation that characterized both parent galaxies will be vastly reduced, replaced by random motions in all directions. The central regions of Milkomeda will be extraordinarily dense by the standards of spiral galaxies. While our Sun orbits in a relatively sparse region of the Milky Way, with perhaps 1 star per cubic light-year on average, the core of Milkomeda might contain hundreds or even thousands of stars per cubic light-year. From a hypothetical planet in these central regions, the night sky would be spectacular beyond imagination. Thousands of stars brighter than Sirius, hundreds brighter than Venus, creating a sky so bright that true darkness would never fall, and planetary atmospheres would be continuously illuminated by collective starlight. But what about our Sun? What's the fate of our solar system during this galactic cataclysm? The answer is both reassuring and sobering. The solar system itself will almost certainly survive the merger intact, but its location within the merged galaxy is highly uncertain and subject to the whims of gravitational chaos. Computer simulations that track individual stellar orbits through the merger show that stars originally in the Milky Way's disk are scattered throughout the merged galaxy. Some end up in the central regions, orbiting within a few thousand light-years of Milkomeda's core. Others are flung to the outer halo, orbiting at distances of 100,000 light-years or more from the galactic center. And, as mentioned earlier, a small fraction, perhaps 5.10%, are ejected entirely, flung into intergalactic space to wander alone between galaxies. Our Sun's specific fate depends critically on the detailed geometry of the merger, which we cannot predict with certainty because we don't know exactly the current tangential velocity of Andromeda or the precise structure of the dark matter halos. But statistical analysis of many simulations suggests that our Sun is most likely to end up somewhere in the outer regions of Milkomeda, perhaps 30,000 to 50,000 light-years from the merged galactic center, farther than our current distance of approximately 26,000 light-years from the Milky Way's center. This repositioning will have profound effects on Earth's night sky, assuming Earth or any remnant of it still exists. Currently, we see the Milky Way as a band across the sky because we're embedded in its disk, looking through the plane of billions of stars. From our new position in Milkymeda's halo, there will be no Milky Way band. Instead, Milkymeda will appear as a roughly spherical concentration of stars centered on one direction in the sky, brightest toward the galactic core, and gradually fading toward the outskirts. Paradoxically, despite being in a galaxy containing twice as many stars as the current Milky Way, the visible night sky might actually contain fewer bright stars than we see today. This is because in an elliptical galaxy, stars are more evenly distributed throughout the volume rather than concentrated in a disk around us. We'll be farther from most stars on average, even though there are more stars total. But there's another critical factor that will affect whether anyone, human or otherwise, will be around to observe this: our sun's evolution. In approximately 5 billion years, about the same time the merger will be completing, our sun will exhaust the hydrogen fuel in its core and begin evolving into a red giant. It will expand to perhaps 100 times its current radius, swelling to a size that will likely engulf Mercury and Venus and possibly Earth. Even if Earth's orbit expands due to the sun's mass loss and escapes being physically consumed, the planet will be subjected to temperatures of thousands of degrees, completely sterilizing the surface and boiling away the oceans and atmosphere. Long before this terminal phase, Earth will become uninhabitable. In roughly 1 billion years, increasing solar luminosity, the sun gradually brightens as it ages, will trigger a runaway greenhouse effect that will boil Earth's oceans and render the planet completely sterile. So while the galaxy merger is unfolding, while Andromeda is approaching, and the first close passage is occurring, Earth will already be a dead world, baked by a sun that has become too bright for life to persist. This means that if any observers witness the Milky Way-Andromeda collision from Earth's orbital location, they will not be residents of Earth as we know it. They might be descendants of humanity that have terraformed or constructed habitats elsewhere in the solar system or beyond. They might be an entirely different form of life that evolved after Earth's biosphere was destroyed. Or quite possibly there will be no observers at all, just a dead or disintegrated planet orbiting a red giant star that happens to be passing through a galactic merger. The merged galaxy will also host a new central supermassive black hole, formed from the merger of the Milky Way's Sagittarius A, 4 million solar masses, and Andromeda's central black hole, approximately 100,200 million solar masses. The combined black hole will have a mass around 200 million solar masses and will settle into the dynamical center of Milkymeda, defining a gravitational anchor point around which the entire galaxy's structure will eventually relax. Milkymeda's future beyond the merger is one of gradual aging and evolution. Star formation will continue for a while, particularly in any gas-rich regions that survive the merger, but the overall rate will decline as gas is consumed, ejected, or heated to temperatures too high for star formation. Over tens of billions of years, Milkymeda will gradually redden as its massive bright blue stars exhaust their fuel and die, leaving behind an increasingly dominant population of long-lived red dwarfs and the stellar remnants of dead stars, white dwarfs, neutron stars, and black holes. Eventually, in the unimaginably distant future, hundreds of billions to trillions of years hence, Milkymeda will become a dark galaxy, its last stars having exhausted their fuel, leaving only cold stellar remnants orbiting in the darkness. But that's a timescale so vast, it defies comprehension. Longer than the current age of the universe by factors of hundreds or thousands. For now, for the next 5 billion years, Milkymeda's birth will be a spectacular cosmic event, the violent creation of a new galactic structure that will dominate the local group for billions of years to come. Here is where we must confront one of the most counterintuitive aspects of galaxy collisions. Despite the spectacular violence of the merger, despite 1 trillion stars from Andromeda colliding with 400 billion stars from the Milky Way, the probability that any two stars will actually physically collide with each other is virtually zero. Not small, virtually zero. The entire merger will occur, the galaxies will be completely restructured, and yet almost no individual stars will ever come close to touching. To understand why, we need to grasp the sheer emptiness of space. Stars are unimaginably far apart compared to their sizes. Our Sun has a diameter of about 1.4 million kilometers. The nearest star, Proxima Centauri, is 4.24 light-years away. That's 40 trillion kilometers, roughly 30 million times the Sun's diameter. If we scale this down to something more tangible, if the Sun were the size of a grain of sand 1 millimeter across, Proxima Centauri would be another grain of sand 30 kilometers away. This vast emptiness means that when two galaxies collide, the stars simply pass through each other like two swarms of bees occupying the same airspace. The probability that any particular bee from one swarm hits a bee from the other swarm is negligible. And the same is true for stars. We can actually calculate this probability with reasonable precision. Consider the cross-sectional area presented by all the stars in both galaxies. The Milky Way's 400 billion stars, if we assume they're all sun-sized, a simplification, but reasonable for order of magnitude estimates, present a total cross-sectional area of about 400 billion times pi times 700,000 kilometers square equals roughly 6 times 10 squared square kilometers. That sounds enormous until we compare it to the cross-sectional area of the galactic disk itself, approximately pi times 50,000 light-years a square, approximately equal to 2 times 10 square kilometers. The ratio is only about 3%. The stars occupy only a tiny fraction of the galactic cross-section. But this calculation is overly generous to the collision hypothesis, because it assumes all stars are arranged in a single plane, and a star from one galaxy encounters all stars from the other galaxy. In reality, the galaxies are three-dimensional, and stars from one galaxy pass through the other at various depths, encountering only a small fraction of the total stellar population. When we account for this three-dimensional geometry and the relative velocities of the galaxies, detailed calculations suggest that the probability of any particular star experiencing a direct collision is on the order of 10 to 10 per star per collision passage. With roughly 1.4 trillion stars participating in the merger, this means we might expect perhaps 1 to 100 stellar collisions total during the entire multi-billion-year merger process. And these numbers are upper limits. If anything, they're overestimates, because they don't account for gravitational focusing effects that cause stars to slightly repel each other at close approaches, further reducing collision probabilities. What this means is profound. The Milky Way Andromeda collision is not a collision of stars, it's a collision of gravitational fields, of dark matter halos, of gas clouds, but not of stars. The stars are simply test particles responding to the changing gravitational potential as the two galaxies merge. Their orbits are radically altered. They're flung onto new trajectories. Some are ejected entirely, but the stars themselves never touch. This is completely unlike collisions we're familiar with from everyday experience. When two cars collide, the metal bodies impact and deform. When two planets collide, as may have happened when the proto-Earth collided with a Mars-sized body, creating our moon, the rocky material impacts and merges. But when galaxies collide, the constituent stars simply sail past each other, their orbits determined by gravity rather than physical contact. There's a beautiful way to visualize this. Imagine two clouds of gnats, each cloud containing trillions of insects, flying toward each other. When the clouds interpenetrate, individual gnats from each cloud pass within millimeters of each other, but actual collisions are extraordinarily rare because each gnat occupies such a tiny volume compared to the spacing between gnats. The clouds merge, their overall structure and motion patterns completely transformed, but the individual gnats remain intact. However, and this is a critical caveat, while stellar collisions are virtually impossible, near misses are not. Stars don't need to collide to gravitationally affect each other. When two stars pass within a few light-years of each other, they can exchange orbital energy and angular momentum, altering each other's trajectories. These gravitational encounters are the mechanism by which the galaxy's orbital energy is dissipated, why the repeated passages gradually slow down, and why the final merger occurs. Moreover, while stellar collisions are rare, stellar systems are not immune to disruption. Stars with planets, stars with binary companions, stars with distant cometary clouds, all these systems can be disrupted by close gravitational encounters with other stars. A star passing within a light year of our Sun wouldn't collide with the Sun, but it could gravitationally perturb the orbits of planets, potentially ejecting them from the solar system or sending comets from the Oort cloud plunging into the inner solar system. The simulations suggest that during the merger, perhaps 1020% of stars will experience close encounters with other stars close enough to potentially disrupt planetary systems or binary star systems. This is not insignificant. It means that a substantial fraction of stellar systems will be gravitationally perturbed, even if direct collisions are vanishingly rare. There is one exception to this general rule of no collisions: the dense galactic cores. In the central regions of both galaxies, where stars are packed much more tightly than in the outer disk, stellar collisions, while still rare, become possible. The cores of globular clusters, the densest stellar environments in galaxies, occasionally experience stellar collisions that can create exotic objects like blue stragglers, stars that appear younger than they should be because they've been reinvigorated by collision-induced merging. But even in these dense environments, collisions are rare events, occurring perhaps once every few million years in a cluster containing hundreds of thousands of stars. So when you visualize the Andromeda Milky Way collision, don't imagine stars smashing into each other like billiard balls. Imagine two ghostly structures interpenetrating their constituent particles, the stars passing through each other without contact while the overall gravitational fields merge and create a new equilibrium configuration. It's a collision without colliding, a merger without merging at the stellar level, a cosmic event of enormous violence and consequence that nevertheless leaves its individual stellar participants almost completely untouched. While the stars themselves won't collide, the gas clouds most certainly will. And when they do, the consequences will be spectacular. The Andromeda Milky Way merger will trigger one of the most intense periods of star formation either galaxy has experienced in billions of years, creating a cosmic fireworks display that will be visible across millions of light years and fundamentally alter the stellar populations of the merged galaxy. To understand why gas behaves so differently from stars during a galaxy merger, we need to recognize a fundamental distinction. Stars are collisionless, but gas is not. Stars are discrete points moving through the gravitational field, interacting only through gravity at a distance. But gas is a continuous medium. Atoms and molecules that can collide, transfer energy and momentum, shock, compress, and heat. When gas clouds from two galaxies collide at relative velocities of hundreds of kilometers per second, the kinetic energy of their motion is converted into thermal energy, sound waves, shock waves, and turbulence. The Milky Way currently contains approximately 1020 billion solar masses of gas, most of it in the form of atomic or molecular hydrogen distributed throughout the galactic disk. Andromeda contains a similar amount, perhaps slightly more. When these reservoirs collide during the merger, the compression and shock heating will trigger star formation on a scale dwarfing anything occurring in either galaxy today. Current star formation rates in both galaxies are relatively sedate, roughly 1 to 2 solar masses per year, meaning each galaxy creates the equivalent of 1 or 2 Sun-like stars annually. But during the peak of the merger, simulations predict star formation rates will spike to 100 solar masses per year, or even higher during the most intense phases. This represents a dramatic increase, transforming both galaxies from quiet, mature systems into starbursts comparable to the most active star-forming galaxies observed in the distant universe. Where will this star formation occur? Not uniformly throughout the merger system, but concentrated in specific regions where gas collisions are most violent and compression most extreme. The simulations identify several distinct phases and locations of enhanced star formation. First, during the initial approach before the galaxies even make first contact, tidal forces will compress gas in the spiral arms, triggering enhanced star formation along the compressed arms of both galaxies. We're already seeing hints of this in real merging galaxy systems. Enhanced star formation begins before first passage, not after, as gravitational compression prepares the gas for collapse. During and after the first passage, gas in the outer regions of both galaxies will experience direct collisions. Two gas clouds moving toward each other at 200,300 kilometers per second will collide and shock, heating to temperatures of millions of degrees in some regions, while compressing and cooling in others. The compressed regions will collapse under their own gravity, fragmenting into dense molecular clouds that will rapidly form stars. These collision-induced star-forming regions will appear as brilliant blue knots scattered throughout the merger system, each containing thousands to millions of newly formed hot, massive stars. But the most intense star formation will occur in the central regions during and after the final merger. As gas from both galaxies is funneled toward the center by gravitational torques, it will pile up in the merged galactic core, creating a massive concentration of molecular gas, perhaps billions of solar masses in a region just a few thousand light-years across. This gas will be turbulent, heated, compressed, and perfect for forming stars. The result will be a nuclear starburst, creating tens of millions to hundreds of millions of new stars in the galactic center over just a few 100 million years. These starburst regions won't just form more stars, they'll form different types of stars than we typically see forming today. The compressed, turbulent gas conditions favor the formation of massive stars tens to hundreds of times more massive than the Sun. These massive stars are intrinsically luminous, shining with the brightness of hundreds of thousands or millions of suns, and they live fast and die young, exhausting their nuclear fuel in just a few million years before exploding as supernovae. The collective effect of millions of these massive stars forming in concentrated regions is transformative. Their ultraviolet radiation ionizes the surrounding gas, creating brilliant HII regions, volumes of glowing hydrogen gas hundreds or thousands of light-years across. Their stellar winds, particles streaming away from the stellar surfaces at thousands of kilometers per second, create hot, low-density bubbles in the surrounding medium. And their supernovae, occurring at rates potentially hundreds of times higher than in quiescent galaxies, inject enormous amounts of energy and momentum into the interstellar medium, heating gas, driving galactic winds, and potentially even suppressing further star formation by blowing gas out of the galaxy entirely. This creates a feedback loop that's both self-regulating and self-limiting. Star formation heats and disrupts the gas, making it harder for additional star formation to occur. The most intense starbursts are therefore relatively brief, lasting perhaps 100,500 million years before the available gas is consumed, expelled, or heated to temperatures too high for gravitational collapse. After this peak, star formation rates decline, and the galaxy settles into a more quiescent state. Observational evidence for these processes comes from studying galaxy mergers throughout the universe. Astronomers have identified thousands of merging galaxy pairs at various stages of interaction, and virtually all of them show enhanced star formation compared to isolated galaxies of similar mass. The most advanced mergers, where the galaxies are in the final stages of coalescence, often show spectacular nuclear starbursts with star formation rates exceeding 100 solar masses per year, exactly what the simulations predict for the Milky Way Andromeda merger. Some of the most extreme starbursts observed in the universe are in ultraluminous infrared galaxies, UAIRGs, systems forming stars so rapidly that they emit most of their light in the infrared due to dust absorption and re-emission of stellar radiation. These galaxies are forming stars at rates of hundreds to over 1,000 solar masses per year, creating an entire solar system's worth of new stars every day. While the Milky Way-Andromeda merger likely won't reach these extreme rates, ULIRGs typically result from mergers of extremely gas-rich galaxies, and both the Milky Way and Andromeda have already converted much of their gas into stars. It will certainly produce a substantial starburst by local standards. The stars formed during these merger-induced bursts will have lasting impacts on the merged galaxy's structure and evolution. Many will form in dense clusters containing thousands to millions of stars in volumes, just a few light-years across. These superstar clusters will eventually evolve into globular clusters, joining the hundreds of ancient globular clusters already orbiting both progenitor galaxies. Future astronomers studying Milkomeda billions of years hence will be able to identify these young globular clusters by their higher metallicity. They'll contain more heavy elements than the ancient clusters because they formed from gas already enriched by billions of years of stellar evolution in both parent galaxies. The massive stars formed during the starburst will also enrich the interstellar medium with heavy elements. When they explode as supernovae, they'll scatter elements forged in their cores, oxygen, carbon, silicon, iron, into the surrounding gas. This enriched gas will be incorporated into subsequent generations of stars, progressively increasing the metallicity of the merged galaxy's stellar population. Billions of years after the merger, the chemical composition of stars in Milkomeda will preserve evidence of the starburst, a chemical signature written in stellar spectra that records this period of intense star formation. To truly understand Andromeda's significance, we must zoom out beyond the galaxy itself and examine its role in the larger cosmic structure it inhabits. The local group, a gravitationally bound collection of galaxies spanning approximately 10 million light-years and containing more than 80 known members, from giants like Andromeda and the Milky Way down to ultra-faint dwarf galaxies barely containing a few thousand stars. The local group is our cosmic neighborhood, the gravitationally bound cluster within which Andromeda reigns as one of two dominant members. The structure isn't centered on a single point. Instead, it's a binary system of two massive galaxies, Andromeda and the Milky Way, with dozens of smaller galaxies orbiting one or both of the giants, plus a few intermediate mass members like the Triangulum Galaxy, M33, that complicate the dynamics. Andromeda is the largest member of the local group, outmassing the Milky Way by a factor of perhaps 1.5 to 2 when dark matter halos are included. This makes Andromeda the gravitational anchor of roughly half the local group. A substantial fraction of the smaller dwarf galaxies are satellites of Andromeda rather than the Milky Way, bound to orbit the larger galaxy over timescales of billions of years. The spatial distribution of local group members reveals the dominant influence of these two giants. The Milky Way and Andromeda are separated by 2.5 million light-years, with most other group members scattered throughout a roughly spherical volume centered between them. But this distribution isn't uniform or random. There's a pronounced concentration of dwarf galaxies around each of the two massive members, creating two distinct subgroups within the larger local group structure. Around Andromeda orbit, at least 14 confirmed satellite galaxies, including the prominent M32 and M110 we've discussed, plus a collection of fainter dwarfs, like NGC 147, NGC 185, and I through and XXX3I, yes. Roman numerals. Astronomers ran out of NGC catalog numbers and switched to a more systematic naming scheme. Many of these satellites are dwarf spheroidal galaxies, small systems containing millions to tens of millions of stars, but virtually no gas, having long since exhausted or lost their star-forming material. The Milky Way's satellite system is comparable in number. We know of approximately 60 satellite galaxies orbiting our own galaxy, though this number continues to grow as surveys discover increasingly faint dwarfs. The most famous Milky Way satellites are the Large and Small Magellanic Clouds, visible to the naked eye from the southern hemisphere, as diffuse patches of light, each containing billions of stars. These are substantially more massive than any of Andromeda's known satellites, though this may simply reflect observational bias. We can detect fainter satellites around the Milky Way because they're so much closer. Between the two giants lies an intriguing third participant, the Triangulum Galaxy M33, a smaller spiral galaxy containing perhaps 40 billion stars. Triangulum's status in the local group is ambiguous and contested. Is it an independent member of the group, orbiting somewhere between the two giants? Is it a satellite of Andromeda, gravitationally bound to the larger spiral? Or is it currently transitioning from independence to capture, about to become a satellite for the first time? Orbital dynamics calculations give different answers depending on the assumed masses and velocities, making Triangulum's role in the upcoming merger uncertain, a topic we'll explore in more detail in the next section. Beyond these major players, the local group contains a menagerie of smaller galaxies. There are dwarf irregular galaxies like IC 1613 and Wolf-Lundmark-Melotte, small systems still actively forming stars and containing significant gas reservoirs. There are dwarf ellipticals and dwarf spheroidals, gas-poor systems dominated by old stellar populations. And there are ultra-faint dwarfs, discovered only in the last 2 decades, systems so faint they contain fewer stars than some globular clusters and are detectable only through painstaking statistical analysis of stellar surveys. These ultra-faint dwarfs are particularly interesting for cosmology and dark matter physics. Despite containing relatively few stars, they're dominated by dark matter. Their stellar velocities indicate total masses far exceeding what their visible stars could provide. Some ultra-faint dwarfs have mass-to-light ratios exceeding 1,000, meaning they contain more than 1,000 times as much mass as their luminosity would suggest, with the excess mass being dark matter. These systems are essentially dark matter halos with a small number of stars sprinkled in, providing natural laboratories for studying dark matter properties in relatively simple, isolated environments. The local group is also notable for what it doesn't contain. Unlike richer galaxy clusters like Virgo or Coma, which contain hundreds to thousands of galaxies, the local group is relatively sparse and isolated. The nearest comparable galaxy group, the Sculptor group, is approximately 11 million light-years away, far enough that there's essentially no gravitational interaction between the groups. The local group is an island, a self-contained gravitational system evolving independently of the larger cosmic structure surrounding it. This isolation is both limiting and advantageous for astronomers. It's limiting because we're stuck inside the local group. We can't observe it from outside to see its overall structure and dynamics the way we can study more distant galaxy groups. But it's advantageous because the relative simplicity of the system makes it easier to model and understand. We can measure individual stellar velocities in nearby dwarf galaxies, resolve individual stars and star clusters, study detailed chemical compositions, observations impossible for more distant galaxy groups, where individual galaxies appear as unresolved smudges of light. The future evolution of the local group is dominated by the Andromeda-Milky Way merger. Once these two giants collide and merge into Milkomeda, the gravitational dynamics of the entire group will be transformed. The merged galaxy will have a total mass approaching 3 trillion solar masses, including dark matter, making it the overwhelmingly dominant gravitational influence in the group. Smaller members that currently orbit one giant or the other will find their orbits radically altered by the merger, with some potentially being flung out of the group entirely, while others spiral inward to be consumed by the merged central galaxy. Long-term simulations extending tens of billions of years into the future suggest that the local group will eventually collapse into a single massive galaxy containing most of the group's stellar mass. The merger of Andromeda and the Milky Way is just the first major event in this long-term evolution. Subsequent mergers will incorporate Triangulum, the Magellanic Clouds, and eventually many of the smaller dwarf galaxies. Building a single giant elliptical, that will be all that remains of the once diverse local group. But this ultimate fate is billions to tens of billions of years away. For now, the local group remains a dynamic, diverse collection of galaxies, with Andromeda standing as its largest member, a gravitational giant whose approaching collision with the Milky Way will reshape not just two galaxies, but the entire cosmic neighborhood we inhabit. The Triangulum Galaxy, catalogue designation M33, third entry in Messier's famous list, is the local group's enigmatic third partner, a galaxy whose fate during the Andromeda-Milky Way merger remains frustratingly uncertain despite decades of study. With approximately 40 billion stars and a mass of roughly 5 times 10 solar masses, Triangulum is substantial enough to potentially influence the merger dynamics, yet small enough that it might be merely a spectator or victim rather than an active participant. Triangulum is located approximately 2.7 million light-years from Earth, making it slightly more distant than Andromeda, but still comfortably within the local group. It's the third largest galaxy in the local group, after Andromeda and the Milky Way, though it's substantially less massive than either giant. Perhaps 1/10 the mass of Andromeda or the Milky Way, when including dark matter halos. This intermediate status makes its role in the merger particularly interesting and complicated. The fundamental question about Triangulum is one of gravitational allegiance. Is it an independent member of the local group, or is it a satellite galaxy already bound to Andromeda? The answer determines its fate during the merger, and unfortunately, the observational uncertainties are large enough that we simply don't know for certain. If Triangulum is truly independent, orbiting in the general gravitational potential of the local group, but not specifically bound to either giant, then its future depends on the detailed trajectory of its orbit. Some simulations suggest it might swing past both Andromeda and the Milky Way during their merger, experiencing gravitational perturbations that alter its orbit, but allowing it to survive as an independent galaxy, at least temporarily. In this scenario, Triangulum would be like a smaller ship watching two battleships collide, buffeted by the gravitational waves of their encounter, but not directly involved in the collision itself. Alternatively, if Triangulum is already a satellite of Andromeda, gravitationally bound to the larger galaxy and executing a long, slow orbit around it, then its fate is more directly tied to the merger. As Andromeda and the Milky Way approach and eventually merge, Triangulum would be dragged along, its orbit around Andromeda preserved but embedded within the larger merger system. In this scenario, Triangulum would eventually be incorporated into Milkomeda, either tidally disrupted and absorbed like other satellite galaxies, or surviving as a satellite of the merged system, depending on the specifics of its orbit and the merger dynamics. Recent observations have provided some clues, but haven't definitively resolved the question. Measurements of Triangulum's velocity show that it's moving toward us at approximately 24 kilometers per second, a relatively modest velocity compared to Andromeda's 110 kilometers per second approach. This velocity is consistent with either interpretation. It could be an independent galaxy with its own orbital motion through the local group, or it could be a satellite of Andromeda with some component of motion toward us due to its orbit around the larger galaxy. Attempts to measure Triangulum's proper motion, its apparent motion across the sky, which would reveal its tangential velocity component, have proven challenging. Triangulum is far enough away that its apparent motion is extremely small, requiring decades of precise positional measurements to detect. Some studies using Hubble Space Telescope and Gaia data suggest Triangulum is moving in a direction consistent with being on a bound orbit around Andromeda, but the measurement uncertainties are large enough that this conclusion isn't definitive. What we can say with more confidence is that Triangulum shows evidence of ongoing or recent tidal interactions. The galaxy's outer regions show structural asymmetries and distortions that suggest it's being gravitationally perturbed by something, most likely Andromeda, given its proximity. Streams of stars and neutral hydrogen gas extend beyond Triangulum's main disk, possible signatures of tidal stripping. These observations suggest Triangulum is at least feeling Andromeda's gravitational influence, even if we can't definitively say whether it's bound to orbit Andromeda or just experiencing a close passage. If Triangulum does participate in the merger, either as a bound satellite of Andromeda or as an independent galaxy that happens to be in the wrong place at the wrong time, what role will it play? Computer simulations that include Triangulum as a third participant suggest several possibilities. In some scenarios, Triangulum undergoes a direct collision with one of the larger galaxies before the main Andromeda Milky Way merger occurs. This could happen if Triangulum is on a plunging orbit that brings it close to Andromeda's disk within the next billion years or so. Such a collision would be spectacular but asymmetric. Triangulum is much smaller than Andromeda, so while Andromeda would survive largely intact, perhaps with some enhanced star formation and structural distortions, Triangulum would be substantially disrupted, potentially destroyed as a coherent galaxy and absorbed into Andromeda's structure. In other scenarios, Triangulum survives until the main Andromeda Milky Way merger begins, then participates as a third body in the collision. This creates a much more complex dynamical situation. Three galaxies interacting gravitationally, each perturbing the other's orbits in ways that are highly sensitive to initial conditions and difficult to predict precisely. Some simulations show Triangulum being flung out of the merger system entirely, ejected by gravitational slingshot effects to wander alone in intergalactic space. Others show it spiraling inward to merge with the combined system, adding its stellar mass to the growing Milky Galaxy. Perhaps the most likely long-term outcome, regardless of the specifics, is that Triangulum will eventually be consumed. If it's already bound to Andromeda, it will eventually merge with Andromeda or Milkomeda through the same dynamical friction processes that cause satellite galaxies to spiral inward over billions of years. If it's currently independent, the Andromeda Milky Way merger will dramatically alter the gravitational landscape of the local group, potentially capturing Triangulum and placing it on an eventual collision course with Milkomeda. The uncertainty about Triangulum's fate highlights a fundamental limitation of our understanding of the merger. We're trying to predict the detailed outcome of a complex gravitational interaction billions of years in the future, based on current observations that have significant uncertainties. The positions and velocities we measure today are snapshots, but predicting how a system evolves requires knowing not just where things are and how fast they're moving, but also the direction of motion, the full three-dimensional velocity vectors, which are much harder to measure for distant objects. For human-scale analogies, imagine trying to predict the outcome of a three-body billiard ball collision based only on seeing a single photograph showing the ball's positions and knowing their speeds, but not exactly which direction each ball is moving. You could make general predictions, they'll eventually collide, but the specific outcome, which ball ends up where, whether they scatter or cluster, would depend sensitively on those directional details you don't have. Nevertheless, the general picture is clear. Triangulum's days as an independent spiral galaxy are likely numbered. Whether it's consumed by Andromeda before the main merger, disrupted during the Andromeda Milky Way collision, or absorbed by Milkomeda billions of years later, the ultimate fate is probably incorporation into the merged system. Future astronomers studying Milkomeda, tens of billions of years hence, will see evidence of Triangulum's consumption in stellar streams, in chemical signatures of its stellar population mixed into the merged galaxy, in perhaps a few globular clusters that once orbited Triangulum now orbiting the much larger Milkomeda, fragments and ghosts of a galaxy that no longer exists. The human relationship with Andromeda stretches back far beyond telescopes, beyond written records, to a time when our ancestors first looked up at the night sky and noticed that faint fuzzy patch in the constellation we now call Andromeda. This isn't a galaxy that required modern instruments to discover. Under dark skies, away from light pollution, Andromeda is visible to the naked eye, appearing as a small, misty spot distinct from the pinpoint stars surrounding it. The earliest written record of Andromeda comes from the 10th century Persian astronomer Abd al-Rahman al-Sufi, who described it in his Book of Fixed Stars, completed in 964 CE. Al-Sufi called it a small cloud, accurately noting its fuzzy, nebulous appearance that distinguished it from stars. This observation places Andromeda among the handful of deep sky objects known to ancient and medieval astronomers, a select group that included the Orion Nebula, the Pleiades cluster, and a few other fuzzy patches visible to sharp-eyed observers under dark skies. For nearly 7 centuries after al-Sufi's observation, Andromeda remained a curiosity noted by various observers but not understood. Was it a cloud of luminous gas, a cluster of distant stars, something else entirely? The technology to answer these questions didn't exist, so Andromeda remained in catalogues as simply a nebulous star or a small cloud, its true nature hidden by distance and the limitations of human vision. The telescopic era began to change this. In 1612, the German astronomer Simon Marius became one of the first people to observe Andromeda through a telescope, describing it as looking like the light of a candle seen through horn. This was a poetic but accurate description. Even through early telescopes, Andromeda appeared as a diffuse glow rather than resolving into individual stars, suggesting it was genuinely nebulous rather than simply a distant star cluster. Charles Messier included Andromeda as number 31 in his famous catalogue of nebulous objects in 1764. Messier was a comet hunter, and his catalogue was essentially a list of things that look like comets but aren't, frustrating false alarms that would waste a comet hunter's time. That Andromeda made this list tells us it was prominent enough and fuzzy enough to potentially confuse visual observers searching for new comets. Throughout the 18th and 19th centuries, as telescopes improved, observers began noting Andromeda's structure. It wasn't uniformly fuzzy, but had a bright central region surrounded by fainter extensions, suggesting a flattened disk-like shape. William Herschel and his son John both observed and sketched Andromeda, noting what we now know are the spiral arms, though the term spiral nebula wouldn't be widely applied until the mid-19th century, when Lord Rosse's Large Reflecting Telescope revealed clear spiral structure in M51, the Whirlpool Galaxy, and similar structure was subsequently recognized in Andromeda and other nebulae. But the fundamental question remained: what were these spiral nebulae? Were they clouds of gas and dust within our own Milky Way? Perhaps solar systems in formation, as some astronomers believed? Or were they separate, island universes? Independent galaxies of stars comparable to our own Milky Way, but vastly more distant, as others speculated. This question sparked one of the most famous debates in astronomical history, the Great Debate of 1920 between astronomers Harlow Shapley and Heber Curtis. Shapley argued that spiral nebulae were relatively small, nearby objects within the Milky Way. Curtis argued they were distant galaxies far beyond our own. Both presented evidence for their positions, but the observational data available in 1920 wasn't definitive enough to conclusively settle the matter. The resolution came in 1923-1924 when Edwin Hubble used the 100-inch Hooker telescope at Mount Wilson Observatory to observe Andromeda with unprecedented clarity. In photographs of the galaxy's outer regions, Hubble identified individual stars, not just blurred light, but distinct stellar sources he could measure and study. Among these stars, he identified variable stars called Cepheids, stars that pulsate with regular periods related to their intrinsic brightness. By measuring the pulsation periods and apparent brightnesses of these Cepheids, Hubble could calculate their distances using relationships discovered by Henrietta Leavitt. The result was revolutionary. Andromeda was approximately 900,000 light-years away, later revised upward to the current value of 2.5 million light-years as distance calibrations improved. This was far beyond even the most generous estimates of the Milky Way's size, definitively proving that Andromeda was a separate galaxy. Curtis had been right. The universe was far larger than Shapley had argued, and our Milky Way was just one galaxy among countless others scattered through space. This discovery fundamentally transformed our cosmic perspective. Humans went from living in a universe where the Milky Way was essentially everything, where the visible nebulae were just clouds within our galaxy, to a universe of galactic islands, where our home galaxy was one among billions, and the true scale of the cosmos was almost incomprehensibly vast. The 20th century brought progressively more powerful instruments and new observational techniques. Radio telescopes in the 1950s and 1960s mapped Andromeda's neutral hydrogen distribution, revealing the extent of its gas reservoirs and rotation. X-ray telescopes beginning in the 1970s detected X-ray binaries and hot gas in Andromeda's halo. Infrared observations penetrated dust clouds to reveal star formation regions invisible in optical light. Each new window on the electromagnetic spectrum added new layers to our understanding of Andromeda's structure and evolution. The Hubble Space Telescope, launched in 1990, revolutionized our view of Andromeda yet again. Free from atmospheric distortion, Hubble could resolve individual stars throughout much of Andromeda's disk and halo, map globular clusters, study star-forming regions, and create detailed images of unprecedented clarity. The famous Hubble mosaic of Andromeda, which we'll discuss in more detail in the next section, represents the culmination of this capability. A billion-pixel image resolving 100 million individual stars across a galaxy 2.5 million light-years away. Modern observatories continue to push our understanding forward. The Spitzer Space Telescope mapped Andromeda in infrared light, revealing cool dust and obscured star formation. The Chandra X-ray Observatory studied its X-ray binaries and hot gas. Ground-based surveys like the Pan-STARRS project have mapped Andromeda's outer halo and stellar streams with exquisite detail. And the Gaia satellite, by precisely measuring positions and motions of stars, has begun determining Andromeda's proper motion, its tangential velocity across the sky, providing critical data for predicting the eventual collision timeline. From Al-Sufi's small cloud in 1964 CE to Hubble's billion-pixel masterpiece in the 21st century, our view of Andromeda has been transformed beyond recognition. What began as a curiosity visible to the naked eye became the key that unlocked our modern understanding of the universe's scale and structure, and continues to be one of the most studied objects in the sky. A cosmic laboratory teaching us about galaxy formation, stellar evolution, dark matter, and the eventual fate of our own galactic neighborhood. In 2015, astronomers released what might be the most spectacular image of another galaxy ever created. The Panchromatic Hubble Andromeda Treasury, PHAT, mosaic, a composite image of the Andromeda Galaxy containing 1.5 billion pixels and resolving approximately 100 million individual stars. This wasn't just a pretty picture, it was a scientific tour de force, the result of 411 individual Hubble Space Telescope pointings assembled into a seamless whole spanning more than 48,000 light-years of Andromeda's disk. To truly appreciate what this image represents, consider the scale. Each pixel in this 1.5 billion pixel image corresponds to a region of space less than a light-year across. From a distance of 2.5 million light-years, Hubble resolves structures comparable in size to the distance between our Sun and neighboring stars. Imagine photographing individual cities on Mars from Earth, and you'll have some sense of the angular resolution involved. The image doesn't cover all of Andromeda. That would require far more observing time than even Hubble's packed schedule could accommodate. Instead, it focuses on a strip extending roughly one-third of the way around Andromeda's disk, covering the northeastern section of the galaxy from its inner regions out to approximately 60,000 light-years from the center. This might sound like a limitation, but this strip contains more stars than Hubble could physically resolve and catalog The 100 million stars identified in the image represent only the brightest, most prominent stellar sources, with countless fainter stars remaining unresolved, even in this extraordinary image. The observations were taken in ultraviolet and near-infrared light, not just visible wavelengths. This multi-wavelength approach allows astronomers to distinguish different types of stars based on their colors and brightnesses. Hot, young, massive stars shine brilliantly in ultraviolet light, making them stand out against older stellar populations. Cool, older red giants emit more strongly in infrared wavelengths. By combining observations across multiple wavelengths, the PATHAT team could classify stars by type, age, and evolutionary state, creating not just an image, but a stellar census of Andromeda's disk. What did this census reveal? First, it confirmed and quantified the distribution of different stellar populations across Andromeda's disk. The inner regions are dominated by older, redder stars, populations that formed billions of years ago when Andromeda's disk was first assembling. The outer regions and spiral arms show concentrations of young blue stars, recent star formation concentrated in regions where gas clouds are compressed and collapsing to form new stellar generations. But the image also revealed unexpected structures and asymmetries. The distribution of young stars isn't uniform along the spiral arms, but clustered into distinct associations and complexes, some containing thousands of hot, massive stars formed within the last few million years. The older stellar populations show subtle variations in density and color that may trace ancient merger events or dynamical processes that redistributed stars within the disk billions of years ago. One of the most scientifically valuable aspects of the PHAT data is that it allows astronomers to construct detailed color magnitude diagrams, essentially plots of stellar brightness versus color for millions of individual stars. These diagrams are the astronomer's equivalent of DNA analysis, encoding information about stellar ages, chemical compositions, and evolutionary states. By comparing observed color magnitude diagrams to theoretical models of stellar evolution, astronomers can determine the star formation history of different regions of Andromeda, when stars formed, how rapidly formation occurred, and how the rate has varied over cosmic time. These analyses revealed that Andromeda experienced a major burst of star formation approximately 2–3 billion years ago, creating a large population of stars that are now in intermediate evolutionary stages. This burst was likely triggered by a merger event, the collision and absorption of a substantial satellite galaxy that injected fresh gas into Andromeda's disk and triggered enhanced star formation. Evidence of this ancient merger shows up not just in the stellar populations, but in structural features like the thick disk and stellar halo, both of which contain stars likely acquired from consumed satellites. The PATHAT mosaic also provided unprecedented views of Andromeda's globular cluster system. While globular clusters appear as single fuzzy objects even in good ground-based images, Hubble resolves them into their constituent stars, allowing detailed studies of cluster masses, ages, and stellar populations. The survey identified and characterized hundreds of globular clusters, revealing a wide range of properties, from ancient, metal-poor clusters nearly as old as the universe itself, to younger, metal-rich clusters formed within the last few billion years. Perhaps most remarkably, the image allows individual stellar spectroscopy for the brighter stars. Follow-up observations using Hubble's spectrographs can obtain detailed spectra of individual supergiant stars, measuring their chemical compositions, temperatures, and velocities. This provides ground truth for our understanding of stellar evolution in different environments. We can see directly how massive stars in Andromeda's metal-rich inner regions differ from those in the more pristine outer disk, testing models of how stellar evolution depends on initial chemical composition. The dataset is so large and complex that it continues to yield scientific discoveries years after its release. Astronomers are still mining the catalog, identifying rare stellar types, unusual variable stars, eclipsing binaries, and other interesting objects among the 100 million catalogued stars. The PAT data has spawned hundreds of scientific papers covering topics from the detailed structure of spiral arms to the properties of stellar clusters to the dynamics of Andromeda's disk. Creating this mosaic required extraordinary technical precision and data processing. Each of the 411 individual Hubble pointings had to be aligned with sub-pixel accuracy to create a seamless image. Challenging because Hubble itself is moving in orbit around Earth, both galaxies are rotating, and various instrumental effects need to be corrected. The raw data volume was enormous, multiple terabytes of images that required specialized software and substantial computing resources to process, align, and assemble. For the public, the P-HAT mosaic has become an iconic image, downloadable in various resolutions, including versions so large that zooming in reveals individual stars as distinct points of light. You can start with a view of the entire galaxy, zoom in to see spiral arm structure, zoom further to see individual star clusters and associations, and continue zooming until individual stellar sources become visible. A cosmic zoom that drives home the scale and complexity of another galaxy in a way that descriptions and statistics simply cannot match. The 2020s have brought a new generation of observatories and surveys that are revolutionizing our understanding of Andromeda with unprecedented data quality and scope. These aren't incremental improvements, they're transformative capabilities that are revealing aspects of Andromeda's structure and history invisible to previous generations of instruments. The Gaia satellite, operated by the European Space Agency, has been a game-changer, despite its primary focus on the Milky Way. Gaia's mission is to precisely measure positions, motions, and brightnesses of stars, creating the most detailed 3D map of our galaxy ever produced. But Gaia doesn't stop at the Milky Way's edge. Its measurements extend to Andromeda's brightest stars, providing proper motions, apparent motions across the sky, for hundreds of thousands of individual stars in our neighboring galaxy. These proper motion measurements are extraordinarily challenging. Andromeda is so distant that even its fastest-moving stars appear to move across the sky by less than a millionth of a degree per year. But Gaia's unprecedented positional precision, combined with observations spanning multiple years, allows these tiny motions to be detected and measured. The result is the first direct measurement of Andromeda's tangential velocity, how fast it's moving across the sky perpendicular to our line of sight, not just toward or away from us. What Gaia found confirms what simulations predicted. Andromeda's motion is predominantly radial. It's moving almost directly toward us rather than past us. The tangential velocity is quite small, meaning a direct collision is indeed inevitable rather than a near miss. This observational confirmation of the collision trajectory is exactly the kind of ground truth that improves our confidence in merger simulations and allows more precise predictions of the collision timeline and geometry. Gaia has also mapped the motions of stars in Andromeda's halo and satellite galaxies, revealing the dynamical structure of the extended system. These measurements show that several of Andromeda's satellites are on highly elliptical orbits that will eventually lead to tidal disruption and absorption. We're seeing the dynamics of galactic cannibalism happening in real time, with orbital parameters measured well enough to predict when various satellites will be destroyed. The James Webb Space Telescope, JWST, operational since 2200, is bringing its revolutionary infrared capabilities to bear on Andromeda. While Webb hasn't yet produced a complete survey comparable to Hubble's PAT mosaic, targeted observations are revealing phenomena invisible to previous instruments. Webb's infrared vision penetrates dust clouds that obscure optical observations, revealing embedded star formation in Andromeda's molecular clouds, regions where the next generation of stars is forming, currently hidden from view at optical wavelengths, but glowing brilliantly in infrared light. Webb has also observed individual evolved stars in Andromeda's halo asymptotic giant branch stars, shedding their outer envelopes in dusty winds, creating circumstellar dust shells that glow in infrared light. These observations are revealing the late-stage evolution of stars in different chemical environments, showing how metallicity affects the mass loss process and the properties of stellar winds. This has implications for understanding how stars enrich the interstellar medium with heavy elements, a process critical to galaxy chemical evolution. Ground-based surveys continue to make important contributions. The Pan-STARRS survey, using a wide-field telescope in Hawaii, has mapped Andromeda's outer halo to unprecedented depths, discovering faint stellar streams and substructures that trace the orbits of disrupted satellites. These observations have dramatically increased the known extent of Andromeda's stellar halo, revealing structures extending well beyond 500,000 light-years from the galactic center, farther than previously thought possible. The Canada-France-Hawaii Telescope CFHT Megacam survey has produced extremely deep imaging of Andromeda's outskirts, identifying individual stars in the outer halo and allowing detailed mapping of the giant stellar stream and other tidal features. These observations are revealing the archaeology of Andromeda's growth through galactic cannibalism, with each stream representing a separate accretion event that can be individually studied and characterized. Radio observations with the Very Large Array and other instruments have mapped Andromeda's neutral hydrogen distribution with unprecedented resolution, revealing complex structure in the gas disk, including holes, shells, and asymmetries likely caused by stellar feedback, supernovae, and stellar winds clearing cavities in the interstellar medium. These observations show that star formation and stellar evolution are actively reshaping the gas distribution, creating structure on scales from light-years to thousands of light-years. X-ray observations with Chandra and XMM Newton have conducted deep surveys of Andromeda, identifying hundreds of X-ray binaries, systems where a compact object, neutron star or black hole, is accreting material from a companion star, releasing enormous amounts of energy in X-rays. The population and properties of these systems reveal information about stellar evolution, supernova rates, and the endpoints of massive star evolution. Surprisingly, Andromeda appears to have a different X-ray binary population than the Milky Way, with fewer bright X-ray sources than expected for a galaxy of its mass. A puzzle that may indicate differences in star formation history or binary star formation efficiency. Recent studies have also provided new constraints on Andromeda's dark matter halo using a variety of techniques. Observations of stellar kinematics, how fast stars are moving at different distances from the galactic center, allow astronomers to map the gravitational potential and infer the dark matter distribution. These studies suggest Andromeda's dark matter halo extends to at least 1.5 million light-years, with a total mass approximately 1.5 trillion solar masses, roughly twice the mass of the Milky Way's dark matter halo. Chemical composition studies, using spectroscopy of individual stars, are revealing gradients in metallicity and element ratios across Andromeda's disk and halo. These measurements show that the inner regions of the galaxy are more metal-rich than the outer regions. Stars near the center have higher abundances of elements heavier than helium than stars in the outskirts. This gradient preserves information about how the galaxy assembled, how gas was enriched with heavy elements over time, and how mixing and dynamical processes have redistributed material. Perhaps most excitingly, the 2020s have brought the first multi-messenger observations of events in Andromeda. When a supernova exploded in Andromeda in 22b1, designated SN 2021 IAJ, it was observed not just in electromagnetic radiation, but also searched for in gravitational waves and neutrinos, though no detections were made in these channels. Future supernovae in Andromeda, observed with the full suite of modern multi-messenger instruments, may provide unprecedented insights into stellar death across the electromagnetic spectrum and beyond. When astronomers measure the chemical compositions of stars in different regions of Andromeda, they discover something fundamental about how galaxies evolve. The galaxy is not chemically homogeneous. Instead, there's a systematic variation in stellar metallicity, the abundance of elements heavier than helium, that decreases with increasing distance from the galactic center. This metallicity gradient is one of Andromeda's most important observable features, encoding information about billions of years of star formation, chemical enrichment, and dynamical evolution. To understand metallicity gradients, we need to remember that the early universe contained essentially nothing but hydrogen and helium, with trace amounts of lithium. Every element heavier than helium, everything we call metals in astronomical parlance, from carbon and oxygen to iron and uranium, was created in stars through nuclear fusion and dispersed into space when those stars died. The first generation of stars formed from primordial gas contained almost no metals. When they died, they enriched the surrounding medium with newly synthesized elements. The second generation of stars incorporated this enriched gas, so they had higher metallicities, and so on, generation after generation, with each cycle progressively increasing the metal content of the interstellar medium. In Andromeda's central regions, this process has been most efficient and prolonged. The inner galaxy has high stellar densities, rapid star formation in the past, and strong gravitational binding that retains enriched gas against supernova-driven outflows. Stars forming in these inner regions incorporated gas already enriched by many previous generations of stellar evolution, so they have high metallicities, perhaps 2 to 3 times the solar metallicity in the innermost regions. Moving outward from the center, metallicities systematically decrease. Stars in the outer disk typically have metallicities around or below solar values, while stars in the far outer disk and halo can have metallicities 1/10 solar, or even lower. The gradient is approximately linear in many regions, metallicity decreasing by a factor of 2 or so for every 10. 0.00200,000 light-years of distance from the center. This gradient tells us several important things. First, it indicates that Andromeda didn't form as a single well-mixed cloud that collapsed and formed stars uniformly. If it had, the metallicity would be roughly constant throughout the galaxy, since all regions would have experienced the same enrichment history. Instead, the gradient shows that different regions have different enrichment histories. The inner regions experienced more efficient star formation and chemical enrichment than the outer regions. Second, the existence of a gradient tells us that Andromeda's disk hasn't been thoroughly mixed by dynamical processes. If stars and gas were constantly circulating throughout the galaxy, smoothly redistributing material between inner and outer regions, metallicity gradients would be erased. The fact that the gradient persists means that radial mixing, while it occurs, is not efficient enough to homogenize the chemical composition across the entire disk. Third, deviations from a simple, smooth gradient provide clues about specific events in Andromeda's history. For example, if a region of the disk shows anomalously low metallicity compared to its neighbors, this might indicate an inflow of pristine gas from outside the galaxy, or the accretion of a low metallicity satellite galaxy that contributed stars to that region. Conversely, regions with enhanced metallicity might indicate localized bursts of star formation that rapidly enriched the local gas. Recent high-resolution spectroscopic surveys have measured metallicities for thousands of individual stars across Andromeda's disk and halo, creating detailed maps of chemical composition. These maps reveal that the metallicity gradient is not perfectly smooth. There are azimuthal variations, variations around the disk at constant radius, and vertical variations, variations perpendicular to the disk plane, that add complexity to the simple picture of radial decline. The vertical gradient is particularly interesting. In our own Milky Way, we know that the thin disk, containing young stars and active star formation, has higher metallicity than the thick disk, containing older stars, which in turn has higher metallicity than the halo. Similar structure appears to exist in Andromeda, with metallicity decreasing as you move vertically away from the midplane of the disk. This vertical structure reflects the galaxy's assembly history. The thin disk formed more recently from well-enriched gas, while the thick disk and halo formed earlier from more pristine material, or incorporated stars from accreted satellites. Element ratios provide additional information beyond overall metallicity. For example, the ratio of alpha elements, like oxygen, magnesium, silicon, to iron, varies in systematic ways that reveal the balance between different types of supernovae. Type 2 supernovae from massive stars produce predominantly alpha elements, while Type 1a supernovae from exploding white dwarfs produce predominantly iron. By measuring these ratios in stars of different ages and locations, astronomers can reconstruct the history of different supernova types and the timescales of chemical enrichment. In Andromeda's inner regions, old stars show enhanced alpha element to iron ratios, suggesting they formed during an epoch when Type 2 supernovae dominated the enrichment. This indicates rapid early star formation. Massive stars lived and died before Type 1a supernovae, which have longer delay times, could contribute significant amounts of iron. In the outer regions, even old stars show lower alpha element enhancement, suggesting slower, more extended star formation that allowed Type Ia supernovae to contribute iron before star formation largely ceased. The metallicity gradient also affects observable properties of stars. Metal-rich stars are slightly cooler and redder than metal-poor stars of the same mass, because metals in stellar atmospheres increase opacity, trapping heat and altering the star's structure. This means that the inner regions of Andromeda, populated by metal-rich stars, appear slightly redder than the outer regions, creating a color gradient that mirrors the metallicity gradient. Deep photometric surveys can map these color variations across the galaxy, providing a proxy for metallicity even without expensive spectroscopic observations. Globular clusters in Andromeda also show metallicity variations that correlate with their positions. Clusters in the inner halo tend to be metal-rich, while those in the outer halo are metal-poor. But there's additional complexity. Two distinct populations of globular clusters appear to exist, with different metallicity distributions and spatial structures, suggesting they may have formed through different mechanisms, or that some were accreted from satellite galaxies that had their own globular cluster systems. Looking forward, future observations will continue to refine our understanding of Andromeda's chemical evolution. Next-generation spectrographs on extremely large telescopes will obtain detailed chemical compositions for millions of stars rather than thousands, creating unprecedented maps of element abundances across the galaxy. These observations will reveal small-scale chemical inhomogeneities that preserve information about individual star formation events, supernova explosions, and mixing processes, allowing us to reconstruct Andromeda's chemical history in exquisite detail and test theoretical models of galaxy chemical evolution against a wealth of observational constraints.